just give it another minute or two for people to file in.
Steve, I can monitor the chat for questions.
Great. All right. I guess go ahead and get started. I'm Steve Yeager, and on behalf of fellow co-chairs Yaga Richter and Kathy Pajan, I'd like to welcome you to this Earth System Prediction Working Group session. I know everyone has seen this, but this is just a gentle reminder to follow the CGD Code of Conduct during today's session. So we've scheduled 7 20-minute talks, leaving time about 5 minutes each for Q&A. We'll have a break around 10 a.m., come back for a couple more talks, and then an update from the co-chairs, and end with hopefully a ample discussion before noon. I just wanted to point out that we did have one change in the schedule. So Judith Berner is now going to be speaking at 9:15, and she switched spots with Dan Amrine, so he'll speak right after the break. So without further ado, I'll stop sharing and we'll jump right in. Nick Davis is going to tell us about sudden stratospheric warming predictions.
Awesome, thanks. You see that all right?
Looks good.
Okay, thanks. Hi, everyone. My name is Nick Davis. I'm in the Wacom group in ACOM, and normally I would be giving a talk or something in the whole atmosphere session, but because of the amazing groundwork laid for this Earth System Prediction Framework by Yaga and her team, Sasha and Jim Edwards, I've been able to come visit you today and talk about what we think is evidence of at least the sort of limited impacts of the January 2021 sudden stratospheric warming. This was an extreme event that really ignited a lot of public, media, and even scientific interest, especially given the extreme cold that occurred in Texas in February. And so we really wanted to leverage the Earth System Prediction Framework at NCAR to try to better understand this event from a predictability and a causality perspective. So the first question is obviously, what is a sudden stratospheric warming? On the left, I'm showing you this plot from NCEP, which is the 2020 to 2021 evolution of the zonal mean zonal wind at 10 hectopascals and 60 degrees north. which is a good proxy for the strength of the polar vortex in the stratosphere. And this background envelope with the dark gray, light gray, and then sort of thin black lines shows you the range of historical observations of the winds at this time. And so you can see that in 2020, winds in red evolved as normal, and then abruptly in January decelerated rapidly to below zero, which indicates a reversal of the temperature gradient in the stratosphere, and stayed below zero for nearly a month before finally recovering. And so these events are driven by wave forcing from the troposphere, and it tends to have some degree of predictability 1 to 2 weeks in advance. The plot on the right is sort of an interesting volumetric way of looking at a sudden warming, where in red, they're showing you the positive winds in the stratosphere, and in blue, the negative winds. And so you can see that the polar vortex begins as this really organized vortex and then begins to break down into these irregular shapes before finally recovering. So these events are typically followed by a particular order of surface impacts. They're often associated with a negative phase of the northern annular mode, indicating an equatorward shift of the jet and a warm polar cap. These are plots from Deng et al., showing you on the top the zonal wind anomalies in the dashed and solid contours, and then the shading shows you the temperature anomalies. This is in the month after sudden warming. So you can see that the stratosphere and upper troposphere warm quite a bit. That's associated with an equatorward shift of the jet. And at the surface, in these sort of boxed regions, these indicate some of the most robust regions where we expect particular weather regimes, including a lot of cold weather over Eurasia and parts of North America, a warm Atlantic, and in particular Greenland and northeastern Canada. In terms of predictability, it actually typically can degrade somewhat in Europe. We expect a sort of particular cold in Europe. However, because of the storminess, it can actually be very difficult to get accurate weather prediction in terms of the sort of day-to-day weather. But it improves in North America, Asia, and the Middle East. So sudden warmings are these cases where we think there are a window of opportunity to essentially gain increases or at least a better understanding of predictability in the month or two ahead. So in this study, we used the CESM2 Earth System Prediction Framework, which has been introduced a few times. It's CSM2 WACM 6 with a prognostic atmosphere, ocean, sea ice, and land components. And the atmosphere and ocean are initialized by nudging the atmosphere to the NASA FPIT data set. And so essentially every week, right before the forecasts are kicked off on Monday, a model is nudged to NASA FPIT and then initialized with the random field perturbation method. The ocean's reinitialized every 5 years to JRA 55 to take care of some drift, and the land is spun up with NOAA NCEP CFS version 2. So there are a set of 5-member hindcasts that are available, but right now there are 21-member, or at least there were over the winter, 21-member real-time ensembles initialized every Monday. So the difficult thing when you want to understand what was or was not driven by the SSW in particular is the fact that when you have a fully coupled atmosphere where everything's sort of set up the way it occurred, the troposphere, the stratosphere, the ocean, the ice, and the land are initialized, all you can really do is characterize the variability and the predictability. In general, it's probably not good to look at, a surface pattern after an event occurred and say, oh, this was due to the sudden warming, because a lot of other things were going on in the Earth system. It's not even clear that the weather regime that drove the sudden warming also didn't set up the weather after the sudden warming. And so if you want to dig in to understand causality, you have to play around a bit. And we came up with this idea of basically not initializing parts of the Earth system to see what happens in these ensemble forecasts. And so we did a couple simulations where we either did not initialize the troposphere or the stratosphere. And so essentially, we just did not nudge the troposphere to set up the initial conditions. So in these so-called scrambled troposphere runs, we initialized just the stratosphere, the ocean, the ice, and the land. And this troposphere during the initialization was just sort of allowed to feel those other components, but it's not, pegged to the observations at initialization. The same thing with the scrambled stratosphere. So we just initialize the troposphere, the ocean, the ice, and the land. And from that, you can start to derive some understanding of, what are the impacts of the sudden stratospheric warming itself? What are the impacts of the tropospheric circulation at the time of the sudden warming? And then you can even just not initialize the atmosphere at all and just initialize the land surface. And in that case, you can gain an understanding of the impact of the ocean, ice, and land surface on the resulting weather regime after the sudden warming. So essentially, we looked at 4 separate 21-member ensembles here with varying degrees of initialization to try to understand what are the robust impacts of the sudden warming. So the first thing I want to do is show you surface temperatures. That's sort of the basic thing we care about when we think about weather impacts from a sudden warming. We're using NOAA CPC as our observational data set, so it's Northern Hemisphere land coverage here. And on the right is the standard forecast. These are all climatological anomalies, so everything's had the climatology removed. So in terms of the observations, what we see here are some cold over Northern Europe and parts of Eurasia, and then a lot of warmth over Canada and the North Atlantic. And the standard forecasts did a pretty decent job of capturing this over the ensuing 2 weeks after the sudden warming. So the standard forecast, where everything's initialized, did predict a cold Eurasia and a warm Northern Canada and North Atlantic. And this is sort of somewhat typical of a negative NAM. So we produced about 50% of the background variability. When we scramble the stratosphere, so we don't actually allow a sudden warming to occur in the forecasts, what we see is essentially the same picture. So it captures the same percent of variance of the observations, and it's correlated with the standard forecast in R squared of 0.95. So essentially, if you wanted to understand surface temperatures in the week or two after the sudden warming, you did not need the sudden warming to occur. They basically played no role at all. It played no role at all. When you scramble the tropospheric initial conditions, so you basically do not initialize the troposphere, what you see is actually an anti-correlation. So I'm just showing you an R squared that's negative. The negative just means that's the sign of the correlation coefficient. So it's actually essentially orthogonal to the observations. You've got cold over North America and some warmth over Eurasia. This is actually quite similar to what you get with the scrambled atmospheric conditions, which kind of tells you a little bit that the surface boundary conditions are actually forcing some of these anomalies that we're seeing in the scrambled tropospheric initial condition forecasts. So we don't think that the stratosphere really had any measurable impact at all on temperatures in the first 2 weeks after the sudden warming. So moving on, we can push the envelope now to weeks 3 to 4. This is sort of a medium scale, sort of sub-seasonal time scale. And so the observations indicate a much colder Siberia and some warmth over Europe and Asia. And again, the sustained warmth over the North Atlantic, Greenland, parts of Greenland and northeastern Canada. Again, sort of a bit like a negative NAM. This is somewhat reproduced by the forecasts, although they had a little bit too broad of cold over Siberia. The R squared really plummets, but that's partly because we're now getting so much divergence in the ensemble members that, the magnitudes and the patterns are just getting washed out. Again, the forecast with no sudden warming, so the scrambled stratospheric initial conditions here in panel D, show essentially the same thing as the standard forecasts. So even 3 to 4 weeks afterward, about 80% of the surface temperature response in the forecasts can be understood without having to consider the sudden warming. And certainly the bulk of the pattern appears consistent with just the troposphere evolving alone without the influence of the sudden warming. However, you've got a very similar correlation with observations, which really indicates some issues with the drift of the ensemble members over time. Similarly, before, the forecast with scrambled tropospheric initial conditions bears some resemblance. to the forecast with scrambled atmospheric initial conditions. But in general, it's still, well, it shows some resemblance. It's actually much more close to the original forecasts. So the forecast with scrambled tropospheric initial conditions, where we just let the troposphere evolve in response to the sudden warming, actually show decent skill. We're still getting the same skill as we did with the standard forecast. So maybe 30% of the temperature variability at the surface was governed by the sudden warming in weeks 3 through 4. But I just want to emphasize, you really would have gotten essentially the same large scale pattern if your forecasts did not take the sudden warming into account. So dynamically, it's worth pulling back to understand why we're getting these different responses. And I think this gives you a good perspective on actually, why the stratosphere was important in a way, even if you didn't see it in the correlations so much. So this is showing you the polar cap geopotential height anomaly. So the average of geopotential height standardized from 60 to 90 north. This is a good indicator of some of these large scale dynamics in the aftermath of a sudden warming. So on the top is Merit 2, and it shows you these high heights in the stratosphere at 10 millibars, indicative of that warm polar cap we expect after sudden warming. It propagates downward to the lower stratosphere at about 100 millibars and periodically couples with high heights at the surface in the troposphere for nearly 6 weeks before finally dissipating. And the standard forecasts capture this out to about 4 weeks, at which point they do not pick up this re-intensification of the high heights at the surface in observations. What you can see is that when we run with scrambled tropospheric initial conditions, the stratospheric anomalies really don't descend that far to the lower stratosphere, and they tend to dissipate much more rapidly. By January 18th, you're already sort of losing those polar cap height anomalies in the stratosphere, but you're still getting the high polar cap heights at the surface. When we run with scrambled stratospheric initial conditions, so we don't have a sudden warming, we've got the complete opposite, very cold heights in the very low heights in the stratosphere. But the troposphere actually induces some high heights in the lower stratosphere here. And so we think what that means is that you need both the troposphere and the stratosphere evolving simultaneously with this negative NAMS signal to drive the downward propagation and sustained high polar cap heights in the aftermath of a sudden warming. You do get that high height at the surface from January 11th to 18th when you scramble the atmospheric initial conditions, which seems to suggest that the land surface was actually an ocean were really important for setting up some of that tropospheric circulation in the aftermath of the sudden warming. So what caused the extreme cold over the US? If we look at the first 4 box plot indicators on the right, this is showing you the temperature anomalies averaged over North America during this cold event. And none of the forecasts that we've shown so far really suggest that there's going to be any cold over North America. None of them are statistically distinguishable. So we ran the model out instead and initialized at February 8th instead of January 4th before the sudden warming. And a standard forecast actually shows some hint of moderate cold over North America. When we scramble the tropospheric initial conditions and allow the stratosphere to just govern the troposphere independently of the troposphere, we actually find that this simulation predicted exceptional warmth over North America. So what we think this means is that there's not evidence to suggest the extreme cold over North America was driven by the sudden warming. And in fact, there may even be evidence that it would have acted to warm North America over the same period in the absence of the troposphere. So I know I'm running short on time, so I'll leave this up and just say, I think forecasts with different aspects of the Earth system left uninitialized can provide near real-time attribution of subseasonal weather. And despite all the signatures of downward coupling, the sudden warming didn't really have a direct impact on surface temperatures or the surface NAM. But stratosphere-troposphere coupling both seemed to work to sustain the NAM. And I think both are critical to predictability. And I think the fact that CSM2 WACM 6 exhibited the best performance during this event of all the models in NOAA sub-X may highlight the importance of an Earth system model for subseasonal prediction. That's all I have. Thank you.
Thanks, Nick. That was great and right on time. So we've got about 5 minutes for questions. You can raise your hand or post in the chat.
I'll keep my slides up just so I can go to the slide I need to for any questions.
Okay, so there's a question in the chat for Chris Cruz. Any idea of how the troposphere and stratosphere interact physically?
Yeah, that's the
Loaded one.
wow. This is yeah, I think this is I would do best to say this is I don't have an easy answer for that, and the smartest people I know that try to understand strat-trop coupling in the aftermath of a sudden warming are still working very hard to try to understand it. There's arguments for how mass is moving around and inducing anomalies. There's arguments for wave coupling and how the sudden warming may shut off wave activity entering the stratosphere, which then feeds back on the troposphere. Those are just a couple ideas out there, but I don't think there's any easy answer yet.
Ayla has a raised hand.
I was just wondering what your take is on it. There's been a couple of papers come out recently, I think Simon Lee and Wright, and they have argued that this warming was important for extreme cold, the Texas and then other things over Greece. Would you say that that's not correct and they've just inferred that without actually showing the causality?
Yeah, I mean, I think the problem is if you have, I'm familiar with the Wright paper. I'm not familiar with Simon's. So I know in Wright, they basically examine some reanalyses and some remotely sensed winds observations and things. And so the problem is if you're trying to get at causality, I don't see how with the standards, model output or with, OBS, you have no way of untangling, was it the tropospheric forcing that drove the SSW that ultimately also set up that circulation regime in the aftermath of the sudden warming, or was it the sudden warming itself? And so I think, statistically, you can do an analysis of a lot of SSWs and say, okay, in the aftermath of these, we expect, cold air outbreaks over the US. When it comes to an individual event, I don't know how you do attribution without at least some targeted model experiments, because you don't have any way to falsify that causality argument. So at least I know this isn't great because none of our forecasts really capture the cold here that was observed. But I think the differential here, the forecast initialized right before the event, where you have the standard forecast and then the one where you've let the stratosphere evolve and sort of where you've put in the sudden warming, but you've let the troposphere stay uninitialized. The fact that those don't get the extreme cold, to me, says either the extreme cold was, so dependent on so many things lining up besides the sudden warming that it's going to be hard to say anything either way about it, or the sudden warming didn't cause it. That would be my perspective, but I don't have a way to choose those. I think at this point I'd be comfortable saying I just don't find convincing evidence that it was associated with the sudden warming.
Yeah, that makes sense.
Yeah.
No.
I think it's hard when you have causality and predictability. They can be really hard to untangle in something like this.
Steve has a hand up.
Yeah, so I was interested in that figure you showed, the Hofmueller of atmospheric temperature across your experiments. It showed that the scrambled tropospheric signal is much weaker even right at the start, right, in the stratosphere. Mm-hmm. So you're initializing the stratosphere, but already within a day, you've lost a lot of the signal in the stratosphere. And I guess my question is, number one, are you having to drift correct these initialized predictions? And if so, can you really assume that these scrambled IC experiments can be de-drifted kind of the same way as all of your other hindcasts, because you've kind of created this Frankenstein initial condition that's going to have all kinds of transients that aren't common across the hindcast. So I don't know how you get around that problem.
Yeah. So yeah, the issue is, so the way we initialize, just to bring it back, is you just don't nudge part of the atmosphere, and so you're letting the model adjust. In that case, you're letting the troposphere adjusts to the stratosphere, but you're never really, well, obviously you're not correcting it for anything. But at least at initialization, there's no like shock to that system. It's not like but I understand your point. There's no drift correction here. It is a bit of a Frankenstein experiment because you're sort of making it so that your initial conditions in the troposphere are really not going to be representative of what was going on necessarily at the actual time of initialization. That said, I do have to say, like, despite the fact that these polar cap anomalies look so different, the temperature anomalies don't necessarily look so different. That whenever you break something down to the zonal mean, it can look like, there's a lot of difference here. But if I go back even to the surface temperatures, in some cases here, things are looking quite similar. But I understand your point that it can be difficult to interpret this, and I'm not even sure how you would correct this for some of these issues. Because we're trying something so kind of unconventional. It's a little dicey to try to, we understand we have to be careful with overinterpretation is what I'm trying to say. But I think if there was a robust effect here from these things, it should probably come out regardless of how hard we beat the drift down.
All right, we probably should move on. Nick, there's one more question in the chat, so maybe you can take that in the chat. Okay. So our next speaker will be Indy Wood.
Thanks, Yara. I'll hopefully share my screen successfully. So thanks for the, as the screen's coming up, thanks for the invite. And I'm going to talk a little bit more from a hydrologist perspective about predictability and what you could do if you had skillful climate predictions to connect them to water management, which is an important new theme for NCAR as it tries to do more actionable science. So I don't need to probably dwell on the importance of S2S hydroclimate predictions. There are myriad applications, from managing reservoir operations to anticipating flooding conditions or optimizing hydropower generation, and so on. The general goal of research over the last 2 decades or so, and particularly some recent projects that we've had with Reclamation and the Corps of Engineers, is to try to improve the relevance of climate forecasts through watershed scale post-processing and analyses, and to try to incorporate climate information through a sort of conditioning process to generate streamflow forecasts that include or reflect the information, and then to take it all the way to the final goal of assessing benefits for water management. So I'll just talk about 2 examples of this work that have been worked on recently at NCAR, the Upper Rio Grande Basin and the Colorado River Basin. But I want to say a few words about predictability first. As hydrologists or people focus on the land surface, we are very interested in the interplay between land initial conditions on the hydrologic outputs and the predictability that's stored in the watershed, and meteorological predictability. So weather forecasting and climate forecasting and how that balances out this initial condition effect. So we also do the kind of attribution studies that Nick was just talking about, and in particular we use an ensemble framework where we look at a very common technique for streamflow prediction, which is called ESP, or ensemble streamflow prediction, in which you have perfect initial condition through spinning up a model and sort of initializing the state, and then an uncertain future condition through driving it forward with boundary forcings from various sources. It could be historical climatologies, or it could be from a climate model. And what you see in this kind of framework is that early in the year, the initial, so if this is predicting April through July spring runoff, and you start predicting it in October and you move forward all the way through July. Early in the year, the initial condition provides very little information. There's a lot of spread in the prediction. And as you go through and into the spring and the melt period, you get a lot more skill in the forecast. And about 12 years ago, I started playing around with scrambling these initial conditions to see how much the uncertainty in the initial condition played out, calling it a reverse ESP forecast, and found that, in fact, you had if you gave it a perfect climate forecast to drive the model and you scrambled initial conditions, you ended up with a climate forecast being very important at the longer leads. But as you get into the spring, the initial conditions, the uncertainty and signal in the initial conditions drive a lot of uncertainty in the forecast. So we can take this through into analyses where we look at gradients of forecast skill as they relate to gradients of in uncertainty in the seasonal climate forecast or the initial conditions. And just note that there are times of year when forecast skill, such as in early in the year, if you're forecasting going through into April, the seasonal climate forecast uncertainty almost has no impact on the forecast skill, whereas as you get into the spring melt period, the climate forecast uncertainty ends up having a big influence on how uncertain the streamflow forecasts are. So I don't really have time to dwell on that kind of study, but it's been picked up in a lot of forecasting agencies to sort of try to understand where investments in seasonal climate forecasts versus initial condition improvement will have a better benefit on runoff forecasting skill. So in any case, the fact that seasonal climate forecast skill is important in the spring is good, because that's when a lot of the forecasting agencies are trying to make predictions for spring runoff. And so they're very interested in climate forecasts at that time. I'm going to talk about one study that was statistically based in the Rio Grande, which is south of us, southern Colorado, northern New Mexico. This was work done by Flavio Lehner, where we looked at prediction for a number of gauges in this basin and noted that over time, if you look at forecast error, there tended to be over forecasting tendency in the recent period of history versus an under forecasting tendency earlier on. So the question was, to what extent is this influenced by climate and potentially trends in climate, such as in temperature and impact on runoff efficiencies in these basins? So we did a study in which we followed another technique that's commonly used for runoff prediction, which is just regression, using land predictors such as snow water equivalent in prior rainfall or flow to predict future runoff, which in hydrology terms is Q. And so in this particular framework, we asked whether if you included information about climate, which you can take from the National Multi-Model Ensemble and or other forecasting systems like the System 4, System 5 at ECM WWF, which capture, these forecasting systems arguably capture to some extent this temperature trend. By incorporating that information, could you improve your streamflow forecast? And that's what we did. And we basically found in that case that you could get sort of a moderate improvement in forecast skill by making these forecasts aware of temperature and temperature trends. So I'll talk about another general approach to forecasting, which is to use seasonal climate forecast from climate models, sort of a dynamic approach. And in this case, we focused on subseasonal to seasonal predictions. And one of the first things to note is that as these predictions are produced by operational centers, they have a very sort of coarse space-time product set that they generate, such as the one on the right. And yet these water managers are focused on very small basins or maybe at the largest, their regional scale versus kind of local watershed scale. and they're focused on watersheds and how the watersheds behave and respond to climate. And in particular, in this particular watershed right now, there's really a very high priority need for information to predict inflows on this Colorado River Basin. So one of the first steps we took was to create kind of watershed scale analyses that we ran in real time using CFS version 2 and National Multi-Model Forecast, and quantifying their scale on watershed scale levels, and doing different kinds of post-processing, which I'll mention really quickly. So for instance, looking at this watershed scale, we find that in general, you have a lot of skill in the early 1 to 2 week period, mainly from the weather forecast scale that degrades quite quickly, especially for precip as we go further out. We did work on this to assess whether post-processing could add some skill. So rather than look at the precipitation temperature outputs of the climate forecast directly, we decompose the climate outputs into different principal components using this sort of partial least squares regression technique, and then train models, and in general find that post-processing can add some skill, particularly in this case for temperature, where in this particular watershed, you can definitely capture more signal using this component-based technique. Less so for precip. If you look around the West, or if you look around the country at this kind of technique, and there are many, many ways of post-processing, you can definitely see that there are places where you can strongly add predictability, and then there are other places, which are shown in gray over here, where the benefits of post-processing are more mixed or don't help. And that's just for this particular technique. It wasn't a large-scale study, but more to show the proof of concept. So then moving from there with these post-process climate forecasts, can we then use those to condition the reservoir inflow forecast in a basin at the scale of, say, the Colorado Basin? So here we used, this is showing the upper Colorado River with inflows into Lake Powell, one of the big storages serving the Southwest water needs. So the question was whether we could do sort of simply condition these streamflow forecast ensembles using information from National Multi-Model Technique, and we used the analog approach that I won't go into. We also looked at the influence of using climate information at sort of regional scales versus even smaller scales to see whether the climate models would have successfully sort of resolve gradients and climate forecast anomalies in the basin that would be helpful, such as sort of north to south, wet to dry, or warm, cold conditions. And in general, what we found in this kind of a study is that compared with this basic ESP technique that I mentioned earlier, which doesn't use climate information, these analog techniques do tend to lower the error in the forecast of the inflows at this regional scale for this reservoir. So these blue and purple scatter plots of the skill metric or RMSE are lower than the ESP ones. And then the question from there is, so what? If you can improve the inflow forecast for these large scale reservoirs, do those actually make a difference for reservoir operations? And so the person I worked with on this, Sarah Baker, she finished her PhD at CU just recently, and she works for reclamation. She has been building this Colorado Basin streamflow forecast testbed, in which you can intercompare different streamflow forecasts and operating policies and run it through a management model, which is called MTOM, and then assess or sort of benchmark different approaches. And this is just a schematic kind of showing what that model looks like. It resolves 12 major reservoirs in the basin, and you feed it in time series of predictions and reservoir storages, and you look at how those evolve with current operating rules. So we use this basin to look at, this is just an example of the kind of things that you look at in a reservoir operating test bed, where if the black line is kind of the observed lake level or pool elevation in Lake Powell, over the years, you can see that it varies quite a bit, and there are certain thresholds that are shown in these dashed lines that are really critical for the operations. For instance, this one here is on the bottom, triggers certain kinds of releases that lead you toward or that can take place in shortage conditions. So it's really critical to be able to know when you're going to cross one of these thresholds because of the large scale impacts on stakeholders. And in general, we find running these tests that the climate informed inflow forecasts do lead to improved predictions of pool elevation. For instance, again, these are the colors from before, but we find that we can lower the error of these pool elevations going out, even forecasting out 2 years. And so that's a significant result. So I'll just stop with that finding and note that there are really ample applications needs for climate forecasts with the stakeholders that we do deal with, and they're in the S2S to subdecadal timescale. So there's a lot of interest in forecasts going out 2 years or 5 years. Forecasts do have usable scale in the context of water management. You have to think of it in terms of hydrologic predictability, and when initial land conditions sort of trump the climate impacts or climate forecast information, that temperature predictions alone, which are more skillful than precip, can be impactful in snowmelt dominated systems, such as in the Western US. This kind of tailoring and post-processing can provide some benefit. So it's worth doing. These formal test beds for benchmarking the forecasts, I think, are really useful in raising awareness about and helping to quantify these benefits for stakeholders. And also having these integrated teams where you work, with climate experts and hydrology experts and water systems experts is a key to keeping this research moving forward. So that's it for me. Thank you.
Thanks, Andy. Questions for Andy?
I'll ask a question, and Andy, do you have a good idea in what format and how do the stakeholders like to get the information? Like, we're running weekly forecasts and we put them on the data online. How do they get their information, and how do you think they would like to get the information if we have information to give?
Yeah, I mean, a lot of the stakeholders are quite sophisticated. So, they will have, computing systems are set up to extract in an automated fashion data but they tend to get it from providers that are almost like intermediate to the climate forecast group. So if it comes down in the form of streamflow, it will come through a streamflow forecasting center that center is able to download and process the climate forecast as inputs into their systems. I think there is a need for this, going back to these kinds of tailoring applications. I think there's a lot of value in bringing climate forecasts that are just more generally served up on a global or national basis down into kind of a watershed context and adjusting for watershed climatologies and things like that. So these anomalies are calculated against something that's a little more familiar to the user. And in fact, NOAA, Esrol, a group over there, has started to pick this up and try to make products like this. So I think tailoring is very helpful, but I think there's a lot of technical capability in the stakeholders to pull data in any format.
All right, thank you. All right, well, I don't see any other raised hands and we're just about at 9:15. So Judith, do you want to go ahead and get started? So Andy, if you stop sharing your screen.
Yep, I'm trying to find it here.
Thank you.
Hi, hello. Can you see my screen?
Yes, with the presenter notes on the side.
Oh, yeah, okay.
Should we just do
This one. It's better now?
Yep, that's perfect.
Thanks. Yeah, thank you so much for giving me the opportunity to speak. I thought I should talk about a Python-based verification package for initialized forecasts that we're developing. We are developing this in the context of S2S forecasts, but we plan to also use it for some of the multi-annual runs. The work that I'm going to show has been almost completely done by Abby J. These Python-based Jupyter notebooks, but it wouldn't have gone without Yaga and Sasha. And on the software side, we are leveraging previous efforts by Aaron Spring and Riley Brady. The verification package is being developed using NOAA funds on this, the grant shown below. I think all across NCAR but also other centers, there is sort of a new approach to diagnostics and maybe even to do science. And the idea is to have a distributed development that is open to the public. Typically, the software is somewhere on a GitHub you can share. And then you can develop it and make a pull request so that your development goes back into the trunk and can be distributed to the greater community. So there's a person that has control of what goes in or not, or some sort of, hopefully it's not a person, but some sort of group of people. Then Python-based Jupyter notebooks are being developed. As a series, a nice thing about these Jupyter notebooks is they're very nice to debug, to look at intermediate steps, and are used for exploration. So this is really more to do science, academic interest. If you want to make it as a routine forecast or verification, you would probably save it as a Python script itself and have it somewhere in your workflow. There is now the opportunity to program parallel code called Dask, including parallel I/O. And so the processing is a lot faster than what is done with last generation diagnostic tools. Obviously, they are related effort. One is the ESDS, the Earth System Data Science here at NCAR. Then we had a software session, it's the Software Engineering Working Group yesterday about diagnostics. And then in AMP, we're developing the AMWG Diagnostic Framework, ADF. And Brian gave a talk about this in the AMWG Working Group. This is to develop mean and variability diagnostics for the atmospheric component, but we're very happy to also work then across the lab to have also the other system components included. So what is different? Why are we developing something else? Well, we have in the initialized forecasts, we have that lead time dependence. And so here I just randomly grabbed two plots, but on the left side is anomaly correlations or skill score shown as function of forecast day. So these are the forecast lead times. And then here on the right is from a paper by Yaga, led by Yaga, where we have here the anomaly correlation here of the NAO index. And this is done as function of forecast weeks. And here in the S2S context, we often have biweekly averages of a metric. And so this lead time dependent is typically not included in climate diagnostic packages. And so we want that here and we're developing it here, but we definitely want to feed into the greater effort in a collaborative way. So what does this package do? Well, it reads in and pre-processes its forecasts. And so the idea is that all of the heavy lifting should be done so that a user, graduate student, or whoever wants to do science with it can then not spend the time with all of the pre-processing and reading the data, but go and look at the science they have in mind. So what we want to do is provide a minimal number of deterministic and probabilistic skill. And the idea is to have the workflow there, you have the parallelization there so that we can do science efficiently. So for the pre-processing, we have the problem that cobbled models drift. And so your climatology will be different with each time, lead time. And typically you only have skill if you compute verification based on anomalies where you have removed the lead time dependent drift. Another thing is that there's temporal averaging. So for example, in the S2S world, you typically compute weekly or bi-weekly averages. And so you have some temporal averaging. And then we are computing deterministic and probabilistic skill scores. And we want to have a minimal set, which is anomaly correlation, root mean squared error. So this is done in ensemble settings. So we want to have the spread. We want to have, and a typical metric used in S2S is the rank probability skill score for tercile forecasts. So that is to assess if I say my week 4-6 forecast is either in the highest tercile or in the lowest tercile. So it's above or below normal. Here is a snapshot from Abby's GitHub page. So it's a number of, the workflow is, it's a number of different Jupyter notebooks. The first one launches the Dask cluster. The second one is we're reading in the forecast and we're building our own ZAR file, our own ZAR store by combining all the forecasts that are typically in NetCDF forecast. The script 2_ generates the model climatology and the verification climatology. Then we generate the member anomalies. And so all of that is this pre-processing. And then the really interesting script is the fourth one where we compute metrics. So this is normally when people in the ESDS world go and they share their Jupyter notebook and they scroll through it and you can get live results. I did not dare to do that. Plus I'm having lots of technical problems with Jupyter Hub personally, because there's a bit of a learning curve to it, a new software. So this is here, the top of the verification script. So first you read in the libraries you need. Then here again, you have this Dask server running. And here is sort of where the user can then say, okay, which verification data do you want? Which domain do you want? Which metric do you want to compute? It then goes and opens these pre-processed files, which are now ZAR files, and does the verification. And something I will talk later about, what you see here is, here we're looking at 3 models, CSM1, CSM2, and Wacom, to compare them. But some of them are started on Mondays and some of Wednesdays. So we had to work around these different start times and have here verification data sets that are aligned with those different lead times. So I think you all know what Jupyter books are, but basically they have these different cells and then you can click through them and then you can, while you click through them, you can, for example, visualize a map of an anomaly correlation. So this was computed with this package. It's in the paper Yaga submitted about CSM2 performance to James. And so here, for example, we show spread and error. The RMS error is shown in the solid bars and the spread in the dash bars for these 3 different models in the 3 different colors. And then we showed for 5 and 10 members because in this particular comparison, some were only run with 5 members, Wacom, because it would have been too expensive otherwise. And so you can see for the different lead weeks, then the skill score for global land, North America, And at the top is the winter season, at the bottom is the summer season. So something we will do for sure is we want to have the state-dependent stratification of forecasts. So in the S2S context, these are large-scale atmospheric indices like the NAO, PNA, the Madden-Julian oscillation, and maybe certain SSWs, certain stratospheric warmings. And so here's a paper, here's a plot by Ferranti et al. And so this is the skill as function of forecast day. And you can see that if the initial state projects onto an NAO minus state, then you have a longer forecast skill. You're more skillful at day 15 than if you are in a blocked state in this particular case. So we plan to implement that. So how are we going to use this? So we will use this at the ASP Summer Colloquium this year. And so at this point, I think we want to get something ready, and then students will be using it, and I'm sure they will be fantastic beta testers finding all problems with it. We will also leverage that for the WMAI S2S challenge. So it's a prize challenge to improve sub-seasonal to seasonal predictions using AI that some of us plan on participating in. And then we have started initial conversations. It would be really nice to adapt it to the SMILE forecasts and to multi-annual forecasts. It should be straightforward to do that. Maybe we should also look at decadal forecasts. I didn't want to finish with the future work. But I wanted to say a little bit something about the challenges as I see them. This is my personal opinion. I find it really hard to decide at which point during development it's good to start sharing the code. You want people to get involved early, so you have more capability and you have more people contributing to it. But obviously, we all know there's plenty of bugs and difficulties. When you're developing code like that, that's meant to be general. And so I find it really hard to decide at which point to share the code. Another thing about this distributed way of working is how to make sure contributors get credit. We are leveraging here a lot of work that has been developed by other people. And so, for example, the large scale indices have been coded by someone, and the alignment of the verification with the forecast data has been programmed. So I think this is a more general issue that we'll need to somehow address as a community. And then here I have the clean code versus useful code. So part of it would be nice to make very clean code where you just maybe compute one metric and you make one plot. However, when we're actually using it, we almost always want to compare several models and look at the differences. So you end up making code that was clean, and it becomes more and more complex and less readable. I mean, this is a general issue. So for example, what we had is we had very clean code doing all these skill scores, but then we went to do bi-weekly, so based on daily data, then we went to weekly averages, and some of the capability in Klimpret, which is an existing Python package we were leveraging, didn't work any longer. And so we had to actually code everything rather than leverage existing packages. So this is sort of a challenge. Then I already showed you the Monday, Wednesday start date. So even while this code was very clean, now that it is useful to make a plot that we might want to put into a paper, it has become pretty lengthy. And then finally, funding and support. So I'm leveraging here NOAA grant to develop that. But if we want to develop it as a community, we also need to look at distributed funding or working in Friday afternoons. And obviously there can't be an ongoing user support if there's no funding for liaison, somebody who takes care of that. And with this, I thank you very much. And there's questions.
Yeah, so there's a couple of questions, and one of them you already touched on, but I'll just read the two related questions. So one from Sanjeev, are these tools available to university community for use? And then how do you plan on coordinating with the Pangeo community?
Yes, so we want to make those publicly available to everyone, including the university. And I'm hesitating to say definite date, but after the ASP summer school, I think would be maybe a good time. And this is not promising any support. Obviously, we're happy to tell you how to use them, but if something needs to be fixed, we might just not have any funding to fix that, or this somehow needs to be bounced through the community. Yes, I definitely want to coordinate this with the Pangeo community. And maybe we can talk offline if there's anything I want to do, but if I need to write somewhere or how to link it exactly, but Ryan Abernathy and people in the Pangeo community are aware of this effort. The next, I just looked at the, So as part of it, we're also trying to Zarify the S2S simulations with CSM, and we have space on the AWS cloud, and that would further make it faster to access those initialized forecasts and for people to then compute cloud, possibly in the cloud or not, at other centers. I think that would be very interesting for people in developing countries who often just don't have the high performance computing to do some of this heavy lifting entailed. And so, but again, we don't have any funding. So we have to all sort of do it bit by bit with existing resources.
Great, thank you. And there's a hand up from Sanjeev. Do you want to go ahead?
Yeah, thank you. This is really great. This will save me like 6 months of my time in doing the research. One thing I was wondering is, you showed us the plot of anomaly correlation. So these are spatially average plot. So if you think about what Dr. Wood was showing, like spatially distributed, what is skill in my basin versus Colorado basin versus Mobile basin. So is there a way like these skill set can be generated in a spatially gridded way, either the regular grid or the sub-basin scale grid?
Yes, no, so this should be readily available. The idea of these books is that we first compute all the skill score as a map with spatial dependence. And then after that, we are subsetting and looking at different regions and at spatial averages. So this is clearly part of the workflow. What we had to do is, I was saying how fast it is, but I mean, we are not software engineers. We had, for some of the plots, we actually had to subset the space like North America before because it became computationally so expensive. But the idea is these notebooks, you can go in and you can plot your spatial maps all along, and then you say, this is the region I want to average over at the very end. So yes, that's all available.
Thank you.
Are there any other questions? Right, well, why don't we go ahead and move on? So Sanjeev, you'll be up next with your talk.
Very good. Can I share my screen? Okay.
Yep, you should be able to.
Yeah, I'll share in a minute. Can you see my screen?
Yep, you can make it full screen if you like. There you go.
Yeah. Thank you for this opportunity. Today I'm going to talk about the seasonal to multi-year soil moisture forecasting. I've talked about pieces of this manuscript at a couple of previous meetings. So finally we decided to publish it. So now it has been published. So if you need more details, you can look into that paper. And I thank all the co-authors for their contribution. I've designed this talk more a forward-looking talk. So, what are the remaining questions and what's opportunity that we can tap into in terms of improving the forecast? So what you see in this plot is the potential predictability of the soil moisture as well as the precipitation over North America that was computed using the DPLE forecast. And you see the brown line that is soil moisture potential predictability skill that is significantly greater than the precipitation predictability skill. So yeah, while taking this paper to the review process, what I learned that this is known to the community that yes, soil moisture has a higher predictability than precipitation. But what is little not very clear is why is that? Why soil moisture has a higher predictability than precipitation? So I will be spending more than 50 or 60% of my time in explaining at least a answer, not the answer. And then when we go to the next, I'll try to answer, have we reached the upper limit of predictability, or what would be like if we get a little better model or a perfect model, okay? So we'll go ahead and get started with the first one, is why soil moisture has a higher predictability than precipitation. So what we said, that paper is the land processes, including soil moisture memory, reemergence, land atmosphere interaction, can transform a less predictable precipitation signal into a more predictable soil moisture signal. So there are a couple of different hypotheses. So I'll go through one by one, and finally, I will also go into like why the precipitation is somewhat less predictable. At least the time scale that we look into, like a seasonal to sub-seasonal time scale. Okay, so what is the reemergence hypothesis? So many of you are expert in the ocean science. So you think about there is a surface layer and then there is a deep layer where a lot of memory resides, and that gives a low frequency climate variability. So similarly, we can also think about the soil moisture processes where there is a root zone where a lot of dynamics take place. And then there is a subsurface layer where the memory is stored. And this has been confirmed using the observation. So on the top right panel, you see the soil moisture observation from the Illinois climate network. And what do you see that I saw the climatology using the color contour, and then the line contour are the variability, and then the depth is shown on the left-hand side. So you see there is a in the deeper soil layer that is 0.5 meter and below, variability is smaller, and then there is a memory that goes like more than a year. And when we get into the top soil layer, that's a root zone, there is a lot of variability, and then there is a seasonal drying as we go into the summer. And what we think that some of these memory that get stored in the deeper soil layer or subsurface soil layer can be get tapped into during the early spring to summer season to give the year-to-year memory. And we did some of the statistical analysis, anomaly correlation, and we do find that as we go into this bottom panel that anomaly correlation decreases as we expect from the AR1 process, but after a year it started increasing, and then On the right-hand side, it's the same, but it's a seasonal cycle. So we have some suggestion that there is a soil moisture emergence, but it remains a hypothesis, means we have not proven it or disprove it. So it's just a concept that we argued in a paper 2 years ago. Second thing you can think about, as if I have a land and I pour a water, it will quickly evaporate, particularly in this kind of heat wave going around. But if I put some sort of vegetation or of plants, then it will offer the resistance. So that will decrease the flow, water flow into the atmosphere. Similarly, as soon as the land will evaporate, it will decrease the gradient of the vapor pressure deficit. In both cases, it will decrease the rate of flow to the atmosphere. In that case, if the rate of flow decreases, then there will be more residence time in the land surface, and then that giving the more predictability of the soil moisture compared to the precipitation. So that's land atmosphere coupling hypothesis. At least this hypothesis, we have tested it using the climate modeling experiment, where we run 2 sets of ensemble experiment, couple and uncouple. And in this plot, you see the difference in the soil moisture memory between couple and uncouple experiment, and in terms of the like one autocorrelation. And we do find there is an increase generally, particularly in the mid-latitude region, both Central North America and part of Mediterranean or Southern Europe, due to the coupling. So at least there is some evidence to suggest that land atmosphere coupling increases memory, particularly in the mid-latitude region. Okay, coming back to the why precipitation is less predictable. So in this case, we looked into a non-parametric metric that is called apportionment entropy. This is a very interesting metric. We wanted to compare both precipitation and the soil moisture using similar metric. And if the number is smaller, this means sub-seasonal to seasonal variability is much smaller. Whereas if number is larger, then that means it's very high. What first thing I wanted to bring to your notice is this color scale is 1 order magnitude greater than what is color scale I'm showing for the soil moisture in the bottom panel, because the things were not fitting. So I simply multiplied it by the 10. And you see there is a lot of sub-seasonal to seasonal variability in the precipitation. Whereas, West Coast, you have the Central North America, whereas the soil moisture variability, sub-seasonal to seasonal variability, is the order of magnitude is smaller than the precipitation. And that gives some suggestion like, because of very high variability in precipitation, it looks like it is less predictable in our prediction system. So what we did is we averaged the precipitation forecast for all the 12 months. And in the top panel, you see the precipitation potential predictability scale at the annual time scale. This is year 1 to year 10 in the DPLE. And in that case, we interestingly found that this precipitation forecast potential predictability scale is comparable to the soil moisture scale. So at the annual time scale, there is predictability of the precipitation. So a way I think about this thing is, if something happens in the Pacific, or the Pacific temperature changes occur, then precipitation respond to that forcing. But if those changes in the Pacific are small, then there is no signal in the precipitation forecast. So that's what it's showing in terms of the annual scale. But in the bottom panel, you find that what fraction of the precipitation variability is explained by the interannual or at the annual time scale. It's a very small fraction of the total precipitation variability is explained at the interannual time scale. So it's less than 10% of the precipitation variability, whereas most of the precipitation variability is found at subseasonal and seasonal time scale. And that's what, like, even if the precipitation is predictable at annual time scale, it doesn't easily translate into its prediction skill at subseasonal to seasonal time scale. So how does the land surface processes contribute to improving the predictability of the soil moisture? So we started with simple water balance equation. Change in the soil moisture is equal to precipitation minus evapotranspiration minus runoff. We did some algebra, and you can come up with the budget of the soil moisture variance, and then it's a combination of 4 different terms. So one is soil moisture memory. Here, this is where the precipitation factor comes in, precipitation and the soil moisture coupling, soil moisture and ET coupling, and then soil moisture and runoff coupling term. And what it turns out to be, like, we computed these terms using the land model data, and we found the other terms are also kind of quite big, at least seasonal, subseasonal to seasonal time scale. Here are some of the number. Memory term is 0.88. This term is 0.31. Again, 0.38, 0.43. So, but these terms are much more predictable. Soil moisture memory, even potential evapotranspiration, and that's how a land surface is able to process a weak soil moisture, a weak precipitation signal, and converts into more predictable soil moisture signal. Okay, so I almost finished with my first question. I think, yeah, it gave a answer to why soil moisture is more predictable than precipitation. Now I'll go into the second question. Have we reached the upper limit of predictability in terms of the multi-year forecast? Yeah, I put very kind of in a very clear sense, my answer is no. Why do I say that? Is what in this plot is saying that you have the forecast lead time in a month, and then what is realized forecast for the soil moisture in this brown color, that is our realized forecast scale. Whereas if we can compute a similar scale using the observation, means the offline land model simulation, and you see there is a big gap between what is these anomaly correlations show in terms of the observation that is shown in the black line versus what is realized in terms of the DPLE forecast. And almost, I would say, like 1/3 has been realized, and remaining 2/3 remains to be the realized. Of course, there are uncertainty in the observation. These 2 black lines are 2 of the CLM experiment, and then the 3rd green line is from the Amsterdam model. That's another soil moisture based product, and there are uncertainty. So all these reconciling these uncertainty as well as improving the forecast skill is what is potential for improving the skill. Where does this kind of big gap comes from? We have some idea. One thing we know that from our analysis, we found that in the DPLE system, the soil moisture initialization does not improve the precipitation skill. So precipitation skill are shown by the blue line here, and that's basically one among, even if we initialize the random initial condition, that is shown by the gray line. And whereas if you compute the same using the observation, you see the black line that is much higher than what is the blue line. Again, there is a gap between what is realized into the system and then what we are finding from the observation. So this is not to me the first showing like there is a weak soil moisture to precipitation feedback into the CSM climate model. This has been here for a while, like this is 2012 paper where they have compared the NAR with the CAM4 and CLM4, and then again you see there is a weaker skill in CAM4 and CLM4. Similarly, there is another paper in 2016, and again, the author did not find improvement in the skill due to soil moisture initialization for the precipitation. So yes, there is opportunity despite all these challenges. This is the forecast for the 2012 drought and in the California, Nevada region, and it shows a good skill. Like you can compare the blue line that is a forecast line compared to the black line that is observation, and it matches very well. So there is an opportunity to develop a skillful drought prediction system using soil moisture state, and which can be relevant for the society. What are the challenges? We know, like we can predict in the past, some of the droughts show good skill, whereas some other drought do not show good skill. So why is that? I do not know. How is the long memory land process are represented in the climate model. Most of the land model have been used to provide the flux to the atmospheric system. So this process is less observationally constrained or has not been paid attention, and I think we'll learn more about the drift in the next talk. So I think I'll end my talk here using the same plot. There is opportunity to improve the forecast skill. So I don't know if I am old enough to put a challenge for the CSM3, but if I were to draw the same graph after 2 years or 3 years, what I would be kind of comparing against is did this brown line improve a little bit? Not here, but at least from this 35%, did it go to 50% or so? I'll end it here. Thank you.
Thanks so much. We have a raised hand from Isla.
I'm just a bit confused about why you think we have the potential to get up to that black line, because doesn't that's relying on skillfully predicting precipitation, which we have a limit on, right? Or am I misunderstanding what the black line is showing? That's offline land simulations forced with precipitation.
No, this is the offline simulation when you correlate the soil moisture anomaly with the soil moisture simulated by the CLM. This is both are comparison between what is the forecast skill realized in the DPLE versus what is we can potentially realize it using the observation. And
right, but you could.
Okay, go ahead.
You can only get to the black line if you could skillfully predict precipitation. Is that correct?
That's certainly a part of equation, and that's certainly a kind of I would say even a major part of the equation. So it's not like one process that will give us. That's why I put like it's CSM3 challenge. It's a land atmosphere interaction. It's teleconnection processes. It's land processes. So it requires a coordination among different working groups to improve, to push that line to even kind of like on the y-axis 50 to 60%.
Okay, thanks.
Steve, do you want to go ahead?
Yeah, I wanted to follow up with sort of the same question. I'm confused by what you're showing here. The DPLE looks green to me. Is that the skill verified against actual soil moisture observations? And have you done the potential predictability analysis of correlating DPLE with the land model simulation that it was actually initialized from, which was drawn from the CESM1 large ensemble, actually? It wasn't initialized kind of to any historical estimate. It was initialized from a free running historical simulation. And so to quantify potential predictability, you'd have to correlate DPLE with that particular land model simulation evolution.
Yeah, so what we do it here in this brown line, yeah, I'm somewhat, color is not very good for me. So this brown line, we use that particular number 34 land initial condition to compute the anomaly correlation of that initial condition with the ensemble average soil moisture anomaly. And in all these like thin gray line, I use the remaining 39 large ensemble initial condition to correlate with the forecast skill. That's why I'm able to say like, yeah, that 34 initialization did improve the forecast skill. We can do the same analysis using the offline land model simulation. And there are different years you can take like initial condition and then how it projects into the several years, like 12 months after for all the year taking from 1980 to I guess 2010 or something like that one I did. Okay, does that answer your question?
Yes, thanks.
All right, thank you so much, Sanjeev. Let's move on to our next talk by Jerry Meal.
Okay. All right, so I'm going to be talking about initialization methods and relate that to model bias drift and effective trends on calculating the skill of seasonal decalar S2D initialized hindcast. That's kind of the first part. The second part are going to be some preliminary results from CESM1 and E3SM V1 on initializing these models with two different methods and seeing how they drift. So I want to acknowledge Ben Kurtman and Sasha, who have been working on that second part, the drifts in the CESM1 and E3SM V1. And Sasha's also been working with Hyan, Doug, Steve, Bill, and Paco on this bias drift trends and calculating skill parts of this. So if you look at the literature, there's a lot of different ways to initialize S2D predictions. These are four of them. I kind of rank them from cheapest to most expensive. The first is the so-called brute force method. And you just take reanalysis products or some observed products, for example, the CFSR reanalyses for ocean and atmosphere, and just basically put that right into the model, interpolate the reanalysis data to the model grid, and those are your initial states and you're good to go. So that's obviously the cheapest and easiest method to use. One that's a little more expensive is, there's variations on this method, the nudging method. So you're trying to relax the model state to some reanalysis product or some other observational source. So you're not exactly at the observed initial state, but you're somewhere close to it in your model initial states. The third, which is a bit more expensive from that, is the one that we've used in NCAR quite a bit, called the hindcast initialization. And you run the ocean model through 5 cycles of 20th and early 21st century climate with the time evolving observed forcing from the atmosphere, and that forcing from the atmosphere gets kind of imprinted then on the upper ocean. And the 5th cycle, when you've run through this 4 times the 5th cycle, you take that, those as your atmosphere or your model initial states for initialized hindcasts and predictions. And this is sometimes referred to as the forced ocean sea ice, or FOSSI. And that acronym is what I'm going to be using today to refer to this hindcast initialization. And then there's the kind of the Cadillac of all initialization methods, using coupled data assimilation, where you're assimilating all available observations in atmosphere, ocean into the model. So that's kind of 4 different methods. And I'm going to be talking about 2 here today, the brute force method and the hindcast initialization method, or the FOSSI method. So I showed this plot on Monday. But just wanted to say a little bit more about it, because this illustrates the bias and drift problem when you have observed initial states, in this case represented by global mean surface temperatures as the black line, and you've got some trend over this period from the 50s to basically present, which is that black, the straight black line. And then you've got these drifted states. So this is from the DPLE. So each of these dots is the ensemble average for the year 1 hindcast, year 2, and so on. And so when you're going from blue to red, that's going from year 1 to year 10. And so the year 10 drifted states are out here. And you can see that they drift somewhere near the uninitialized or free running simulation from the CESM1 large ensemble, which is this green line. And you see a couple of things in this plot, which I pointed out on Monday. One is these drifts are pretty large and they're pretty rapid. So the model, even though if you started out close to the observations, it really wants to drift away to its preferred state, which is somewhere here in this uninitialized kind of realm, which is a product of its systematic errors. So the systematic errors in the model are making it want to go away from where you've started it out close to the observations. So that's one thing. The other thing is that if you look at the trends, in this case from the DPLE, from the observations, and from the drifted states, to see that the magnitude of the trends are different. Now these trends introduce a lot of different issues, and they're more acute or most acute for the S2D timescales, because if you imagine you're computing anomalies for predictions or hindcasts relative to the average model climatology of the drifted states, the average of that model climatology is going to represent something here around 1990. So that if you're calculating anomalies for a hindcast that's up here closer to present, you can see that the verification that the anomaly you're going to compute is going to contain a lot of this trend. And that trend is going to be somewhat similar to what we saw in the observations. So you're going to introduce enhanced skill just due to the trends. And it's especially going to be bad or most pronounced in the early and the late periods where you're going to have enhanced skill due to the trends. Now, this isn't as big a problem for the S2S or S2AI timescales, because on S2S, a lot of times S2S is only using a climatology of 18 years, so the trends aren't that big. S2I, for example, the NMME project, they were using a climatology of 30 years. But for a big initialized hindcast set on the S2D timescales like the DPLE, you've got 62 years. So you've got a lot of time for these trends to develop and affect how things come out. So I'm going to be talking about bias as the difference between model initial state and the observations. This is literally what the states are the day you start running the model. And the DPLE, these are November 1st start dates. So if you take the model state on November 1st and the observed state on November 1st and take the difference, that's going to be the bias. The drift is going to be the differences that develop after the model starts running. So as the model runs, it's going to drift, and that's these kind of represented by these dots here. So that is how I'm defining bias and drift. So if you look at the bias now, in the DPLE, these are for the November 1st start dates for, in this case, 1979 to 2010, where we have pretty high quality sea surface temperatures. And it'd be similar for other time periods as well, but this is just to illustrate that the bias on November 1st with the model initial states and the observations from that start period have this kind of a pattern. And you can see these biases are pretty big. They're kind of approaching 1 degree C. Off the west coast of the continents here, South Africa, South America, and North America. Got some big positive biases in the North Atlantic and the North Pacific, and you get this kind of banded structure here, which is probably related to the position of the Antarctic circumpolar current. But this is what you've got because you haven't initialized the model directly with observations, but you're initializing it with this FOSSI method or this initialized hindcast method. So by definition, you're not going to be directly relatable to the observations, but you're going to have some drift or some bias already in it. And this is the bias and the pattern. It has a pattern. And of course, when you're looking at brute force, by definition, brute force, this field would be nearly zero because you're initializing the model to literally the observed initial state. So if you relate this now to the drifts, so here's this plot again, I reproduced it over here. This is the bias for the DPLE. Now these are the drifts for the early period from 1955 to 75 in the DPLE, the first month, first year, third year, fifth year, and seventh year. And this is for the first kind of part of the hindcast. This is for the 1980 to 2010 part of the hindcast. And this is the difference between the early and the late periods to assess kind of what the difference in the trends are, what the trend differences mean to this pattern of drifts. So if you first look at this early period, you can see here, this is basically the same pattern you see here. So in the first month, you haven't gone too far away from the initial bias, but by the time you average the first year, the drifts in the first year, now you start to see this kind of these anomalies growing here in the mid latitudes, negative in the Northwest Pacific and Northwest Atlantic, negative in the subtropical Atlantic, and developing this negative bias here, a drift in the equatorial Pacific. As you get to year 3, now these, of course, the colors get darker because the magnitudes of these, the drifts get bigger, but the pattern pretty much sets up early, and the pattern stays pretty much the same. And so the model is going really quickly to its preferred systematic error state, and then that just kind of grows as you go along. And so when you look at the later period, you see a very similar pattern to what you see in the early period. What's kind of interesting are the differences between the early and the late period. And if there was no difference in the trends between these two, this field would be nearly 0 for all of these time periods. But of course, it's not, because there are differences in the trends. And you can see the year 1 difference, you actually have this kind of warmer anomalies in the tropical Pacific and in some areas of the Indian Ocean. But as you go along, things go more negative. And that's because when you're earlier in the period, the early minus late, you're going to have more positive differences. And because the drifts in the early period are more negative, when you get the early minus late differences, you're going to see more negative anomalies here. But it does have this interesting pattern that is a product of the systematic error state in the model that's probably unique to each model. So when you're actually computing anomalies, and this relates to what Judith was talking about, there's various ways of doing this. The more kind of typical way of doing this that all timescales use, from S2I, or S2S, S2I, and S2D, is you difference your prediction from some kind of drifted model, or the appropriately drifted model climatology. So if you have a hindcast for your average for years 3 to 7, you average all the years 3 to 7 drifted model states and form a climatology over the entire time period and do your differences that way. But the problem there is, as I noted earlier, the trends introduce enhanced skill estimates for earlier and later in the hindcast period. And so that's kind of a caveat that accompanies this method. And as I mentioned, it's more kind of acute for the S2D timescale with the long climatology. Another method we've used at NCAR is to try to get away from this effects of the trend, is you bias adjust the predictions, and then you difference that from the previous 15 years from observations. The idea being you've bias adjusted the predictions back to some that were close to the observed state. You've taken the bias out, and you can difference that from the previous 15 years from observations. And that addresses this problem of trends in the data in the model record, but you can also introduce unrealistic skill if the low frequency variability in the observations is large compared to the hindcasts on timescales greater than 15 years. So that's kind of a problem with that method. So we propose something that kind of takes elements of both of these and take the differences compared to the previous 15 years from the start date for each start date with the model initial states. And this gives you somewhat lower skill because you're taking away any artificial enhancements you may have coming from these other two methods. But it does remove the problem of these long differences in long-term trends. And we can actually see how that actually works here. This is another plot I showed on Monday to kind of show that verification for this initialized prediction we made out into the future that was going to verify in the future after the model, after the paper was actually published. And indeed, we were predicting, and that prediction was for CCSM4, we were predicting something transitioning to the positive phase of the IPO, which actually ended up happening. So luckily for us, that ended up panning out, that our prediction actually verified after several years of waiting around for it to verify. But this is just to show the differences in what you see in these patterns, the verification patterns, using different methods of calculating anomalies. This is now the method calculating kind of the standard method where you calculate the anomalies relative to the entire model climatology. You can see that a lot of these colors are red, indicating that there's probably a trend coming in here from the warming from greenhouse gases. And you see this in the observations as well, because you're doing the same kind of thing. You're calculating it, and there's a lot of trend in here. But the verification is pretty good. It's 0.86 because you're getting a lot of skill just from the trend, the fact that everything's warmed up in the model and the observations. This is now this method calculating relative to the previous 15 model years, which is removing elements of this trend. You actually get a nicer pattern here. We can see the positive phase of the IPO. So you're not getting the effects of the trend. However, the pattern correlation, anomaly pattern correlation is a bit lower because you remove the effect of the trend here. And this is the method we were using before compared to the previous 15 years of the observations. We're seeing something similar. It's not quite as, it's a little bit larger amplitude compared to this other method, but it verifies quite well at 0.82, which is something similar to what we got from the 0.86 verification for the pattern correlation for the entire climatology. But this middle one is probably the more accurate representation for the S2D timescales of what the skill actually may be. So now we're going to look at this effects of these two initialization methods in these two Earth system models. So we're going to look at the CSM1. This is the DPLE version, the kind of a 1 degree class Earth system model. Your E3SM, which is the new DOE Earth system model, is a 1 degree atmospheric model that's similar or comparable to the atmospheric model, the CAM5 that was in CSM1. They've made some changes to it, but it's still relatively close to the CAM5. But the biggest difference between these two models is in the ocean. The E3SM V1 has this MPAS ocean, which is a very variable resolution ocean model. It has resolution from 60 down to 30 kilometers. So we're going to use each model with two initialization methods. We're going to get 4 combinations, and these are all initialized at November 1st of each start year. The CSM1 FOSSI is the DPLE, which we've already shown results for. Of course, we have a lot of ensemble members for that, but these 3 new ones that we're running now are the CSM1 with the brute force method, E3SM with the FOSSI method, and E3SM with the brute force method. And so far, we've only got 4 start years with these, with 5 ensemble members each. These are in production, so I've got an asterisk here. These are now running with more hindcasts, with more start years. We're going to have 6 more start years at least. So we'll have a total of 10 start years with 5 ensemble members each, at least initially. And one of the goals of this exercise is to see if we can actually learn something by using fewer start years. And so we can put in more variations, and so we don't have to run an entire DPLE for every initialized hindcast sensitivity experiment. So we're hoping that we can actually learn something using fewer numbers of start years, so we don't have to, so we can save on computer time and still learn something from these things. So let's see how these things are behaving. So this is going to be the month 1 drift. This is the CSM1 brute force, E3SM brute force, CSM1 FOSSI, which is the DPLE, which we've already seen, and the E3SM FOSSI. So if you look at the 2 brute force anomaly patterns here compared to the 2 FOSSI methods, you can see that the anomalies are a lot smaller here in the brute force because the model is only run a month. So you haven't gone that far from your initial state, which was by definition initialized to the observed state. The 2 FOSSI methods, of course, have bigger anomalies because you're starting further away from the observed state. You can see right here that these patterns are already somewhat different between the CSM1 and the E3SM1. So it does seem to make a difference as to which ocean model you're actually using and how these drifts are manifested. Now, this is the year 1 drifts. So the CSM1 brute force and the E3SM brute force are still fairly similar. They still haven't drifted very far from the observed initial states, but the 2 FOSSI models, their patterns are somewhat different, but you can see the anomalies are still a lot bigger. But this pattern here that's now setting here into the E3SM FOSSI, now you can see it showing up here, pretty much the same pattern. And it's pretty much the same pattern that's now set in here in the E3SM brute force version. And so it looks like in the E3SM, at least, by the time you get to the 3rd year, no matter which initialization method you use, you're going to end up with about the same drift anomaly pattern. But for the CSM1, comparing the brute force with the FOSSI, you see it's a little bit different. You're getting kind of warmer anomalies here in the southern hemisphere and in the tropics compared to what you're getting in the FOSSI here with the kind of cooler equatropacific SST and cooler tropics. And if you now go to the year 5, the 2 E3SM versions are still pretty much the same pattern. So that pattern hasn't changed a whole lot, but there does seem to be a little bit of a difference between the CSM1 brute force and the CSM1 FOSSI. And so the big caveat here is that we still haven't finished running all these simulations with the brute force and the FOSSI realizations. And so these are giving us at least some initial indications that the brute force definitely has smaller drifts than earlier on. But by year 3 and 5, you get a similar magnitude and pattern of the drifts in the brute force, FOSSI and E3SM and E3SM, but there seem to be some differences in CSM1. So to summarize, these drifts between the drifts definitely are one of the biggest challenges, and they're a product of the systematic errors in the models. And the biases in the drifts and the difference in the trends can cause issues with how you calculate anomalies to verify skill in S2D predictions. We looked at 3 different ways of calculating anomalies and figured out, or advocating that maybe the differences from the previous 15-year average from observations may be the most accurate of the 3. And then we showed preliminary results with these 2 models with 2 different initialization methods, showing that there's different behavior with the models, with 2 different ocean models, and that the E3SM seems to have very similar drifts with the 2 initialization methods, but there seem to be some differences in CSM1. Thanks.
Thank you very much, Jerry. Are there any questions? Ayla has a question. Go ahead, Ayla.
I was just wondering about the North Atlantic with your 15-year method. It seems like the skill is way down there, and I guess you'd expect that because it's low frequency, and so removing the 15 years, you're kind of removing some of the signal. But is that kind of the right way to judge the skill? I guess it's the skill relative to persistence is kind of more what you're showing with that method.
Yeah, right. So this is just, yeah, with persistence, I think the point here is that persistence was persisting kind of this negative phase of the IPO and kind of a cooler North Atlantic north of 20 north, say, whereas all the verifications show that the North Atlantic cooled and warmed up kind of here in the subtropics. And this is kind of what we can see here in this method where we're looking relative to the previous 15 years, so that we're maybe getting a better look at what's going on in the Atlantic and some areas of the Pacific. But you know, again, this all these methods have problems, and the biggest thing we're dealing with is the model drift and systematic error. So anything we do is basically we're trying to mitigate as much as possible the negative effects from the model drift.
Okay. Thanks.
There's a question from Steve. Go ahead, Steve.
I'm muting here. Thanks, Jerry. That was really interesting. I'm wondering, you know, you mentioned that you're doing the small sets of sensitivities, so you don't have to rerun the full DPLE, but how then do you compute a robust drift correction from, say, 5 starts? Yeah, well, hopefully we're going to have 10 starts, but yeah, this is an issue, right? So this is what we're going to test. We're going to see if we can, and we have the DPLE to compare to, so we're going to have the, for the CSM1 at least, we're going to have the smaller number of starts for the brute force, and then we can actually subsample the DPLE to get the smaller number of starts for the FOSSI. But yeah, this is we're going to see if this works. That's obviously going to be a caveat for any of these kinds of methods where we're trying to figure out ways of learning something about initialized hindcast where we don't have to run a full DPLE and spend all those computer resources. So if we can actually get something out of a fewer number of start dates that we can actually learn something, I think that would be a great kind of way to use these as tools to look at some of these things without having to spend the computer time. But you know, it may not work, so we'll have to see how it comes out.
Jerry, this is Tony Rosati. I just have a question. Why can't you do it the same way we do in seasonal forecasting? Just use the last 30 years or 20 years or something as the period. It's the forecast for the decadal thing that you're looking at.
Yeah, so that would be basically analogous to this middle panel here, where you were computing the anomalies relative to the previous 15 years, which is closer to what S2S and S2I use, right? Right. And that's quite a bit different from using the whole 62-year climatology from the DPLE, which is this top panel here. See, and that's where you really see the effects of the trend coming in here, because it's kind of warming up everywhere, and that's just coming from the trend. And when you take the effects of the trend out, you still have a little bit of the trend in here, but you're getting more of kind of a pattern with positive and negative anomalies. So yeah, I would say that this method would be closer to what is being used for S2S and S2I.
Yeah, exactly. And I don't see what's wrong with in your forecast, including trend.
Well, that's
I mean,
that's
okay. It's part of what the forecast.
Yeah, I think it's, and the trend is fine, and that gives you some skill. But yeah, I think you have to acknowledge the fact that for this particular prediction here, you're getting a lot of the skill you're getting is from the trend.
No, but going back to your 15-year one.
Yeah, right.
Yeah.
Right. So I think that the idea would be, we know we can get skill from a trend, right? But the question is, how much skill are we getting from this internally generated variability? And that's kind of what we're hoping to get some skill from.
Right. And the way I look at it with the lead dependent drift removal, that what you're saying is that basically it's linear. And so that is an assumption that we're making in that anyway.
Yeah,
that,
so I think,
and
yeah,
you're right. The other parts of it would be wouldn't be included.
Yeah, so I think initially you'd say, okay, this is a linear trend, but trends usually aren't linear. So you could come up with ways of, kind of some kind of quadratic fit to figure out if you can capture the non-stationary base state a bit better. So I think initially we're just going to think it's a linear trend, and then maybe think about better ways of calculating that as we get further into it, see if we can get anything out of it.
Thanks, Jerry.
Yep.
Okay, well, we're almost on time, 5 minutes late. Yaga, should we go ahead with a 15-minute break now and come back at 10:35 and hope to make up time?
Sure, either that or we come back at 10:30. Up to you.
All right, we can come back at 10:30 and we might get started a few minutes late, but all right.
Good, see you all
Everyone back.
soon. So I haven't asked Sasha how well our model is doing with this heat wave that's going on right now. There may be another good case study for everybody.
Yeah, that'd be great to look at that.
Yeah, I'll see. We used to have the let me ask Sasha. We still have the weekly plots going.
Well, it's hard to tell if people are back from break yet or not, but maybe we can get started with Dan Amrine's talk.
Sounds good.
Dan's back.
Sounds good. I put all the jokes at the end so people won't miss them.
Yeah, we've got up to 46. We had about 63 before.
I saw as high as 65. I occupy myself by keeping track of how many people are online.
All right. Can you guys see my screen?
Yep.
And the slides change?
Still the title slide.
Okay. Still the title slide?
Yep.
No changing?
Yeah, it's changing.
Oh, okay. Excellent. All right. Well, thanks a lot, everyone. I wanted to take this opportunity to share some recent work with data assimilation in CESM for the questions of initialized predictability that have already come up several times today. I want to acknowledge a long list of collaborators here. This is a cross-lab effort at NCAR that's benefited from interactions with folks both in CGD and in the data assimilation research section as part of CISL. So an outline of this is I want to talk, sort of open up briefly and add to what has already been said about some of the motivations and objectives for data assimilation and Earth system predictability. Talk about some efforts that we have slated for the near term in terms of what we'll call loosely coupled data assimilation product for initializing S2S studies in ocean extremes. Talk about some initial results, comparing some of these DA results to the FOSSI cases. And then talk a lot about future directions, and sort of emphasizing that this is hopefully an opportunity to solicit feedback from folks about what things they most want to see with some of these efforts. So in this community, we've talked a lot about how initialization is a potentially important component of predictability across climate time scales. I guess I say potentially, because maybe there's an awareness that at some time scales and for some problems where you start the model is really important, and for long time scales, maybe it becomes less and less. But a demonstration of this came from the FOSSI runs, sorry, not from FOSSI. FOSSI initialized predictability runs. This is a figure from the 2018 DPLE paper showing that forecast scale is increased in a statistically significant way for ocean heat content in some parts of the ocean relative to an uninitialized ensemble. And so when we think about how to improve initialization or why initialization is important. And Jerry already talked about some of these things, but I guess these challenges have kind of at least 3 components for how we want to initialize a predictive ensemble for ensemble forecasts. On the one hand, we want to start off with an initial state that is relatively accurate relative to the system that we are trying to predict. So if you're trying to predict the Earth system, you'd like to have some sort of initial state that reflects that system as well as you can. But at the same time, we want to make sure that we are also reducing initial shocks and drifts when we start to let our model go. So if you really pin your initial state to something that really looks like the physical system, but the model doesn't want to reproduce that, it lies on another attractor, then you can have some initial shocks or some drifts that can be detrimental to your forecast. And then finally, we're interested not just in initializing a particular state, but also to have a spread of initial ensemble members that reflects our uncertainties in the initial conditions, because we want those uncertainties to be propagated further into our forecast. And so this kind of motivates, these things taken together motivates the sort of what Jerry called the Cadillac of these data assimilation approaches that incorporate observations into the predictive model and give us explicit uncertainties. I usually drive this to work, but now for stay at home, I just park it in the driveway and work with the air conditioning on. There's been an ongoing effort to do data assimilation in CESM, including for the goal of initializing decadal predictability and predictability in other timescales. And in a 2015 paper by Alicia Karsbeck and co-authors, they found that when comparing data assimilation initialized and hindcast initialized forecasts to uninitialized forecasts, kind of reflecting some of these results that I showed earlier from the DPLE, that's really the only places that you see changes in skill are coming most strongly in the North Atlantic subpolar gyre. And that in particular, there weren't a lot of strong advantages of data assimilation initialized states as opposed to the sort of hindcast or Fosse runs. And the authors pointed out that there were a number of caveats here, and I've kind of added to the list a little bit. There's relatively low number of predictive ensemble members in this case. There are persistent problems with the model being biased, which could sort of reduce the efficacy of having data assimilation. This is also a time period, 1961 to 2005, where the ocean data, so this, I'm sorry, I should have said this was for an ocean data assimilation product. So the ocean data are relatively sparse. So you can imagine as you sample the system better and better that the data assimilation would improve. But in a way, I think this poses a challenge for us to moving forward, identify the ways in which we think that data assimilation, which we know theoretically should be the best way of initializing, where that really shows up. And so I wanted to highlight, one possible particular, possibly rosier picture when you initialize not with a data assimilation product, but in sort of a perfect model predictability experiment. This is from a recent paper by Liu and co-authors. You can see higher scale in larger parts of the ocean, although I want to have the caveat that they use a different significance criterion here, so it might not be completely apples to apples. But I guess I wanted to sort of raise the specter that, as model, so that in a way there's a reduced impediment for this study, right? Because it's a perfect model experiment. We don't have to worry about model bias, and it's a limiting case of a perfect initial state. Just to say that as model biases are reduced in the future, being able to accurately, address or have an assimilated initial state that reflects the true system could become more and more important. So these conversations that we've had, I guess over the past 18 months of being at NCAR, I guess I've kind of come to think that the objectives that we can be looking at right now for data assimilation and Earth system prediction are a few. First, to kind of evaluate which processes and timescales benefit from data assimilation initialization for predictability, and thinking about why. I think there's a lot of interesting science questions there. But also acknowledging that we don't expect this necessarily to be a one and done, where there can be a single experiment and we say, oh, data assimilation works, or maybe we don't need it. But acknowledging that this is an evolving process, and so maintaining a test bed to continue these experiments moving forward. And then, also acknowledging that this is part of, some broader efforts on the part of ESPWG to think about seamless prediction, having sort of a unified framework across timescales. And also, this just really dovetails naturally with data assimilation efforts that are ongoing at NCAR as well for other purposes. So I wanted to focus a little bit on these first two questions and to think a little bit about what this actually looks like. What bases should we have for testing data assimilation efficacy? And so, one of the things that's come up, maybe the first order thing you would like to do is to have a sort of DA initialized ensemble hindcast skill measure, a sort of data assimilation DPLE. The advantage of that acronym is that it might be pronounceable, but it also sounds like tadpole when you're holding your nose, over a large span of time. This would give us statistics that we could compare the DPLE, but there's a major challenge in that, certainly the hindcast experiments are expensive, but the data assimilation experiments to run, coupled online, full eNKF are quite onerous. It's a large cost and a lot of person hours in order to make that happen. And so, while we could hypothetically run this experiment if we got the time, the computer time, it's difficult to iterate and think about that as a framework for, as we improve data assimilation or tweak some knob, how can we look at the predictability there? So at least in the short term, I think what we've landed on is the notion of kind of leveraging existing processes to generate shorter reanalyses, focusing on maybe shorter prediction timescales and also some test cases of particularly representative or thorny problems. And also in the background, thinking about data assimilation approaches that would allow us to iterate more quickly and to try to turn the crank and do some of this development work to turn these things around more quickly in the future. And so what these goals are looking like, or how they're manifesting in the short term, are what we're calling a kind of loosely coupled ocean atmosphere reanalysis. And so this term was coined at the very, I've seen it at least in this Carr-Speck et al. 2013 paper, sort of loosely coupled means that you are, in this case, forcing an ocean model where you're doing data assimilation with an atmospheric state where data assimilation has also been performed. So this is in opposition to weakly and strongly coupled. Basically, it comes down to varying degrees to which data in one domain, atmosphere or ocean, affect the state in the other. So this, in a way, is kind of the weakest form of that. And so in this case, we're leveraging the existing CAM6 DART atmosphere reanalysis that we have over 2011 to 2019. And there are some questions that we would like to address with this run. First of all, Jerry has talked a lot about the difficulty or challenges in computing drifts. One question we have is whether or not this is a long enough run to be able to compute those drifts accurately. And then, so we're thinking of then using this as a basis for doing predictability experiments from some of the S2S protocols. And then also looking over this time period over a couple of test cases, which might be particularly apt. One of them is this 2015 North Atlantic subpolar gyre cold blob, which in this recent publication by Liz Maroon and co-authors, basically this subpolar gyre cold blob is a feature that evaded the DPLE and also a number of other ensemble members that these co-authors ran to try to get it. And so, some of the questions posed by this paper are, is this a function of initialization error? Is this a rare event, just extremely rare because it's, the large ensemble is able to produce things like this. So that's kind of an interesting test case that would be, we can go after. And we can think about other test cases, which are also, unfortunately, blobs of one form or another. I do think that, Yaga was mentioning that maybe a test case for shorter timescales. A great community conversation would be what a sort of battery of cases might look like for these longer term prediction timescales. And also just a quick reference to this talk we heard on the plenary talk on the first day about justice in climate science, thinking maybe about test cases that aren't mostly affecting people in England and the University of Washington. So I think a large part of my point here or goal is to communicate sort of the workflow that we're arriving at in terms of studying these problems. And acknowledging that I'm kind of short on time, I'll just say briefly that we're using the ensemble adjustment Kalman filter in both the atmosphere and ocean. So to do this schematically, you have your model simulations running in parallel. When you have observations, you sample the models like the data, compute model data misfits, and adjust the model state by adding an increment, and then forecast the model forward in time until you encounter another observation. And so in the case of the CAM6 DART reanalysis, this is over the time period 2011 to 2019, as I mentioned. We're doing 6-hourly assimilation of millions of observations a day from a range of different sources. This is nicely documented in a white paper by Kevin Rader et al. That I'd encourage you to look up. I would emphasize for atmospheric predictability that this is a data assimilation product that is in CAM6. And so, exciting tool in its own right. For the ocean data assimilation component, we're looking at POP2. I want to emphasize that a lot of really awesome work has been done to document doing data assimilation by the DART group. It's a great sort of gateway drug for data assimilation if that's something that you're looking into. So we're looking at the nominal 1 degree POP simulation with 80 ensemble members forced by the CAM6 80 ensemble members. And these assimilations are slated to be completed this fall as part of a CSL proposal, along with some of these initialization coupled experiments. All right, again, apologies, I'm going very fast, but I did want to just contrast a little bit some of these DA ocean ensembles that we get from data assimilation with the FOSSI to think about how predictability experiments might be different depending on whether you're using one or the other to start. So in this case, I just grabbed a state from the upper ocean. So this is the upper ocean temperature. On the top, I'm showing from the POP data, this loosely coupled data simulation, and on the bottom from the FOSSI simulation. And by eye, these things look extremely similar. If we look at the differences, we can see that there are differences on the order of up to maybe 5 degrees C between these states. I should point out this is the FOSSI at this particular date after 5 times cycling around. So this is conceivably a state that you would use to initialize a predictability experiment. And so these two states are different. We can see that. But another thing we want to look at is how this difference kind of compares to the standard deviation or the spread across our ensemble members that we get from data assimilation. And so here I'm showing an example of this spread from this particular time. So in this case, the spread from the DA ensemble members is quite tight. And so if you were to plot the normalized difference between POP and FOSSI, the differences are extraordinarily large. So at least in this case, I think we can make the argument that FOSSI and POP are statistically different. And we might expect that at the very least, this initialization procedure using the POP DA as opposed to FOSSI should at least give us some different results, not necessarily improved ones. I think we'll have to stay tuned for that. All right, so I'm at the end of my time. I just wanted to emphasize some future directions and kind of put these on the map. It would be really fantastic if people are interested in working on any of these directions. I think that's kind of the best way of working forward, is finding cool problems that need some of these solutions and collaborating on those. Particularly, what tools do we have to kind of crack the problems that we're looking at? This recent data assimilation effort by CSIRO is doing some kind of unorthodox things in terms of sampling atmospheric data for coupled reanalysis, or only doing monthly increments. There are less expensive data assimilation approaches that we're interested in applying, maybe leveraging some capabilities from other data assimilation approaches. and also a lot of interesting work to be done on diagnosing and reducing model bias, which is a persistent problem in data assimilation. All right, so I'm just going to go ahead and leave these objectives up here, and thanks everyone for your attention. I welcome your questions.
Thanks so much, Dan. Are there any questions? Here's one. Go ahead, Sanjeev.
Yeah, thank you. This is very good introduction. And have you thought about like collaborate? I know there is a new scientist who started even in the land group for that land part of the data assimilation. Have you thought about including even the land part of the data assimilation? Particularly on the land part, there is some interest on the how do we, if we incorporate the observed vegetation state and how it would impact even kind of like, yeah, those kind of drought prediction or the heat wave. So is there some collaboration with the land group?
Yeah, absolutely. I know that there's a lot of really active work being done between DART and CLM. And so it's exciting, I mean, especially because my impression is it wouldn't add very much to the cost. Exciting to think about incorporating the lands data assimilation, I guess, potentially alongside the ocean DA. That's not a conversation I've had explicitly with anyone, but especially, I guess, for some of the reasons you're mentioning, that would really be cool to talk more about.
So there's a comment from Will Weeder that he thinks the scientist you're referring to is Brett Roska, who's joining DART.
Yeah, that is right.
Okay.
I was referring to the Brett.
All right. There's another question from Jerry. Go ahead, Jerry.
Hi, Dan. So you mentioned there may be some methods that would reduce the computational expense of coupled data assimilation or the methods you're using. I was curious if there was any kind of new developments there that would make this kind of more feasible to use?
I mean, I think one of the more promising approaches, I wouldn't say is a new development, is what was used by Fred Castruccio for the 10th degree POP ocean-only reanalysis, which is to do this ensemble optimal interpolation. So instead of having error covariances that are updated through time, you have a static error covariance. So that's a direction that we've been pursuing. I guess one thought, or interest, the thing I've been looking at is whether we can leverage large ensemble simulations to get ensemble covariances that would help that problem. So yeah, I think that's maybe one of the more interesting. I would say that at that point, maybe it's not the Cadillac, maybe it's kind of the Buick. They still make Buicks, I don't even know. We expect the scale to be lower, but basically you reduce the cost by, in this case, 1/80th, because you're only running a single ensemble member. So that's something I'm really excited about.
Okay, thanks.
I think we need the Tesla though. Anyway, we're at 10:54, so why don't we go ahead and move on to the next talk? Will be by Matthew Simpson.
All right, thank you. Let's see here. Okay, are you able to see my presentation in full mode?
Yep.
All right, thanks. All right, so I'm Matthew Simpson. I'm a staff scientist at Scripps, specifically working under the Center for Western Weather and Water Extremes, or CW3E. And today I'm going to be providing a project overview for generating a high vertical resolution CESM data set for S2S prediction research. So this project is a collaboration between NCAR and Scripps, and I've got all the team members listed here to make sure that they're all acknowledged. We do have one team member that recently had a job change, now working with the National Institute of Water and Atmospheric Research in New Zealand. That's Peter Gibson, so I want to make sure he gets acknowledged as well. So it's great having such a large team. The result is you get a diverse background and expertise for obviously climate modeling, but also mesoscale dynamics, and for expertise and high performance computing to help with the large number of simulations we're going to be making. So it's great being a part of such a large team with so much expertise. So moving into the motivation for the research. So existing seasonal forecast skill can be low over the Western United States. So anything that can be done to improve these seasonal forecasts, particularly precipitation and drought, is going to be highly advantageous to water resource managers. And to highlight that point, I've just got an image on this slide of the Lake Powell water level. I took this image just 2 days ago, showing the massive drop in water level there. And so any predictions of is it going to improve or get worse with time is highly valuable to the water resource managers. So recent evidence is starting to suggest that stratospheric processes like QBO could be a very important source of S2S predictability within this region. So motivation for our research is to be looking at what impact could increased vertical resolution have on representing these stratospheric processes, and mainly the QBO, and will this result in S2S predictability improving in this region, but also globally. So to just rephrase our primary research question is, does a better represented QBO via increased vertical resolution and dynamical models, does that improve our seasonal forecast skill? And to demonstrate kind of our logic for the motivation here, on the bottom, we've got a 3-panel image showing a time series of zonal mean flow in the trophics that demonstrate the QBO development and oscillation. So on the far left, we've got the observational baseline from Era 5 reanalysis. And so again, what we're looking at is a zonal flow as a function of height or pressure with time. And in the observational baseline, you're seeing a well-developed QBO signature. In the middle, we've got the Wacom model, and this represents kind of the current high top model with weak QBO signature, especially in the lower stratosphere. And one reasoning behind that could be that just insufficient vertical resolution to be resolving the full amplitude of the QBO at relevant heights. And on the far right, we've got increased vertical resolution with a new grid. So this is higher vertical resolution in the stratosphere. And this is showing a much greater QBO signature, and particularly the amplitude. So our thinking is that if we can improve and perform a large number of simulations with this increased vertical resolution, to start to understand the feedbacks on QBO development. Okay, so getting into the specifics of our research methodology and on the run setup, we're going to be using the CSM2 model, which is the same version that's currently used in the SMILE framework. For the grid configuration, we're going to be using a 1 degree lat-long horizontal grid, and we're going to have 2 different vertical configurations. One we're calling the low top and the other a high top, and I'm going to talk in greater detail about the vertical configurations on the next slide. In terms of initialization data, we're going to be using the same ocean and land data that's used to initialize SMILE, but for the atmosphere, we're going to be using JIRA 5 instead of ERA 5 data set. And our reasoning there is we need data going up sufficiently high to initialize our high top vertical model configuration. The period of our hindcast is we're going to be going from 1970 to 2020, so covering 5 decades for the hindcast. We're going to do initialization months going from September to February, and we will be initializing on the 1st of each month. And we will have a 12-month forecast horizon for all these simulations. And to account for uncertainty, we're going to be consistent with SMILE framework and have 20 ensemble members and using a random field perturbation method to generate those ensemble members. Okay, so moving on specifically to the vertical configuration within our research methodology, we're going to be running 2 experiments, as we were calling it, low top and the high top. And to demonstrate the difference in these configurations, the image on this slide is showing the vertical grid spacing as a function of pressure and height. And so for the low top model or experiment 1, the vertical grid spacing is shown in gray. And this is representing the default CSM2 configuration. It's got a model top of 40 kilometers, and within the troposphere and lower stratosphere, the vertical grid spacing is around 1,200 meters. Moving to experiment 2, or the high top configuration, this configuration is now shown in red on the image. And there's 2 key differences here with experiment 1. So for experiment 2, we've increased the model top up to 80 kilometers, and the vertical grid spacing has been significantly reduced in the troposphere and lower stratosphere to 500 meters, making it far better resolution than the default CSM2 and the WACO model, which is shown in black here. And also wanted to make a note that we are adjusting the vertical grid spacing in the troposphere, lower stratosphere, but we are not modifying like the default vertical resolution in the PBL for our project. Okay, so obviously making so many simulations over a large period of time is going to require a large amount of computational resources. So this is where supercomputing that's available to CW3E is coming into play. So CW3E and the San Diego Computer Center, we kicked off an agreement beginning on April 1 under this year that we would obtain majority use of one of their supercomputers called Comet. So initially we only had 65% capacity, but that's going to be increasing to 100% in just 2 weeks from now. So Comet's a large supercomputer with 440 million CPU hours, which would translate to about 12,000 years of CPU on your average laptop. And we currently have 20 projects running on Comet. So it is being used significantly as we speak. So as part of getting access to the supercomputing, and a supercomputing advisory group was set up with CW3 with numerous collaborators, one of which includes NCAR. And the goal of this working group is really just to make informed decisions and recommend high impact research that aligns with CW3E's mission to use the supercomputing resources. Okay, so we're hoping that there's going to be numerous benefits to the S2S community from this research. From a generalized standpoint, I mean, just improved understanding of the impact of the vertical resolution on S2S forecast skill, I think is a good finding and beneficial in itself. And even more specifically, understanding how that vertical resolution translates to QBO predictability over a 12-month forecast horizon could be of great benefit. We also are hoping to explore QBO impact on the surface quantities that really matter the most to decision makers and to society. Obviously, now the Southwest is going through droughts. We've got a current heat wave going on. So understanding that relationship between QBO and how that's translating into the quantities we care most about could be a benefit coming from the project. Also hope that we could really set a standard on an optimal run design for S2S predictions by performing our analysis with the higher vertical grid spacing. Another key component of the project is developing a large database that we're going to make available to the community. So we're hoping that this community data set could be used for predictability studies on increased vertical resolution and to hopefully improve simulations of QBO and MGO connection. And then lastly, this large data set that we generate could also be used for a training data set or machine learning based algorithms on S2S studies. So really hoping that there are multiple areas where this research could benefit the community. So moving on to the current status of our project. So our NCAR collaborators have successfully ported the CSM2 model to the Comet supercomputer. Because we're making so many simulations and taking advantage of the supercomputer, NCAR collaborators install workflow manager Silk on comment, and this is just really to automate the runs as much as possible and to optimize the use of the high performance computing resources that we have. Next, we've downloaded and regridded all the required initial conditions to perform our simulations. We've conducted a series of test simulations that have been successful, just to demonstrate that the model is running correctly, that the workflow is set up fine, and everything seems to be working. And then lastly, the current status is that we've finalized our list of output variables. This has really been kind of an iterative procedure on thinking about what are the variables that we want for this project, but also what are variables that could be used for analysis for other projects going on. So that's really taken a lot of input from different scientists. And again, it's been an iterative procedure, but I think we've got a good list of output variables that we want to work from now. And then moving on to next steps. So we want to submit and complete November runs, just specifically the November runs for all years of experiment 1, or the low top experiment, and then perform initial quality control of these simulations. And our logic here is that we just want to start with the November runs, verify that everything is working, we're getting good results, we're seeing signals that we expect, before moving on to the full suite of simulations. And from a rough estimated timeline, I hope that we can accomplish this in July and August of this year. So as I said, once we've done a quality control of the November simulations, we would be running the full suite of low top cases. I hope that we could get that done by around November of this year. Next step would be to perform an analysis of the model results, see what we can start learning from the low top cases. And we should have that done by the end of the calendar year. And then the next step would really just be to repeat the whole process, but now looking at the high top cases. And so that's going to be a little bit more computationally expensive with the higher vertical grid spacing and levels. But hopefully we could get that done around spring of next year. And lastly, prepare a manuscript documenting all the research findings and the comparison of the low and high top simulations, and really documenting what impact that vertical resolution is having on QBO evolution. So I will be glad to take any questions.
Thank you so much, Matthew. Are there any questions? There's one by Will. Go ahead, Will.
I'll just go ahead and ask it here. Yeah, I was curious if you had the restarts that you need for all the components. I don't know if specifically on land we saved monthly restart files for the Smile. And if we didn't, then I guess we need to do that.
I will let one of my collaborators answer on that. I'm assuming that we have all the initial conditions from what I've been told to make the simulations, but if maybe if Ela wanted to,
yeah, I think
speak on that.
I think Nan has already made them. Yeah.
Will, we did save monthly restarts from Donica's run.
That was fortuitous. Excellent.
And I have a question. Will there be a possibility for the broader community to get involved once you have the simulations done?
I would hope so. I mean, I feel like we're still working on a long-term storage plan for the data. It's no issue storing all the runs currently on our comment system. But where will the data eventually be stored? I hope it's community-based and really could lead to a lot of collaboration with groups outside of VinCar scripts. So absolutely.
Excellent.
I think that's really one of the major benefits of this work, is generating such a large data set that someone that may not have access to a supercomputer could do research that they would want to.
That's great. Thank you. Any other questions?
I was just going to make a comment. It wasn't clear from your talk, but your low top experiments will essentially mirror SMILE just with different atmospheric initial conditions, right? So the low top that you're running, we use ERA 5, whereas SMILE use JRA 55. That's the only difference.
As I understand it, yes.
So in the worst case, we'll just have more ensemble members of the same thing if there are no differences. There's a question in the chat from Jaime. How does the QBO act as a source of seasonal predictability for the Western US? Through what process? Could you please share references?
Yeah, I would have to defer to a QBO expert on on the team on that mechanism. I'm not sure if Jai Bao is on. I think she could speak on it.
Yeah, so Jaime is one of the people who also looks at QBO teleconnection. I think why she's asking because the mechanism for Western US in particular may not be clear. So there's lots of QBO teleconnections to the MJO, so possibly through the MJO, possibly through the polar vortex and the NAO. But I think Jaime maybe can just jump in that focus on the Western US may not be very clear where that comes from.
Yeah, I guess we are clear that the QBO can have a sub-seasonal impact for most, but for the seasonal impact, like we have some studies that the QBO can modulate the storm track or the jet directly, so that can also impact over the Western US through the storm tracks or the jets, but I'm not, but that's the study that have been done by me and Hami, but I'm not sure if other groups that they have other studies about the QBO impact on the seasonal predictability.
Yeah, and I think this will be one of the frontier studies because there are not that many seasonal prediction models that actually have a QBO in them that is any good. So, you know, I think we'll find out whether there are any impacts. All right, in the interest of time, why don't we go ahead and move on? So Steve over here will give a co-chairs update and then we'll follow up with discussion. So as he's talking, I encourage you to think of questions that you might have for discussions and either start putting them in the chat or we'll have opportunity for discussion when he's done.
Okay. So here's what we'd like to update you on. First, some S2S updates, and then bring everybody up to speed on where we're at with SMILE. And finally, talk about the CSL allocation, current usage, and future plans. So I wasn't sure, Yaga, if you were going to present these S2S slides or if you want me to run through them.
You can go ahead.
So this is sort of a summary of what Yaga presented on Monday, outlining our recent S2S hindcast sets using CESM2. Got two versions, one with CAMP 6, one with WACM 6, both at 1 degree horizontal resolution. And these are weekly hindcasts that span 1999 to present. And I think both are being updated in real time. Correct me if I'm wrong. So for the CAM 6, these are 11-member ensembles, and for WACM, 5-member, and they are 45-day hindcasts, and the plan is to keep going through the end of summer. I think this is with real-time updates and thereafter as human resources permit. So Yaga has a paper submitted that documents these reforecasts. I don't know what lost in review means.
It's been a couple of months now. We haven't heard anything. So COVID reviewing timescale.
Yeah. So so this is the documentation paper for this data set, which is already, I guess, available on Campaign Store. at these DOIs, and maybe we can make this available to the whole working group so that you can get access to this data. We brought up at the winter working group meeting the idea of an analysis registry, just to try to bring some coordination to the analysis of these large community data sets. So this is the S2S analysis registry. Maybe Yaga can put the link into the chat. So several people expressed interest, but not all are actively working. Now that this data set is soon to be documented, it's really more urgent now to get serious about trying to put your name down, to put a placeholder on a particular topic that you'd like to look at, so that we can avoid duplication of effort. And then now that these base experiments are done, there's a plan for some additional simulations. So Isla and Yaga have a SNAPSI project, stratospheric nudging and predictable surface impacts. And I guess the idea is to do additional case studies of sudden stratospheric warmings, mixing the initialization, as we heard from Nick this morning. So 3 case studies, and these are almost done with 50-member ensembles, and will be submitted to the SNAPSI project. And then we had put in the CSL proposal the idea of additional S2S experiments to investigate sources of predictability. So I think this is work that's underway. The idea will be to repeat the S2S full hindcast set, but with climatological conditions, in this case, climatological ocean, to investigate the role of ocean variability on S2S predictability. Yeah, so ICs are made, runs to start soon, and then the idea would be to do a similar set of climatological initialization, swapping out the land state. I thought I would give a broad overview of the SMILE experiment. I went over this in the winter, but there may be new people in the meeting today who haven't heard what SMILE is. So we've heard it's invoked several times now. It's our new seasonal to multi-year large ensemble using the CESM2 model, all components at nominal 1 degree resolution, and it includes biogeochemistry in the ocean component. So the MARVEL is turned on. And the design is that we initialize 4 times per year. So November, February, May, and August from 1970 to present. And we wanted, as a requirement for initial condition generation, to be extensible both forwards and backwards, ideally to pre-1960 and forwards to near real time. And we're running these as 20-member ensembles, integrating them for 24 months. And so we have, I'll get to where we're at soon, but I wanted to mention some configuration differences from the CSM2 CMIP6 runs, the historical SSP 3.7 runs. So SMILE uses a different ocean deep isopicomal mixing parameter. It's got other BGC tuning parameters changed relative to those historical runs, a modified sea ice albedo. It's got a bug fix in CLM5, and it uses the smooth biomass burning forcing that we've heard about this week. But there are fewer differences with the latter 50 members of the CESM2 lens ensemble. So those last 2 differences in red are eliminated when comparing SMILE to these member lens. As far as initialization, we're trying to use a consistent set of states based on the JRA 55 reanalysis, and the rationale is starts in 1958, so pretty far back, and is updated in near real time. It's relatively high resolution at 55 kilometers, and it's the basis of the new OMIT-2 forcing for ocean and sea ice models. And so what we're doing in SMILE is just a brute force initialization in the atmosphere, interpolating JRA 55 to the CAM grid. And then for the land, we are making the SMILE trendy run. And this is thanks to Danica Lombardozzi, who's run this, that involves a spin up from equilibrium to equilibrium, and then using crude JRA forcing up through 2018 so far. And in the ocean and ice and ocean biogeochemistry, we're using a FOSSI initialization strategy using the OMIT-2 forcing. And so I'm happy to tell you that the base set of hindcasts from 1970 to 2018 was completed last month. Huge thanks to Nan and Sasha, who were the real heavy lifters here. But I also wanted to call out everyone who's helped in the design and implementation of this experiment. In particular, Hu Kim, Keith Lindsay, and Danica Lombardozzi, who really helped to create the initial conditions that were used. So currently underway, we're extending the November start dates to 10-member decadal prediction runs, so 122-month length hindcasts. And we are looking at doing the forward extension of SMILE to near real time. And we'd really like to get out to May 2021 so that we can put out an actual 2-year forecast that, that might actually be useful. So I thought I would just show some very preliminary results. And as I said, we just finished this base set last month. And so take all of these results with a grain of salt. But here's an analysis that Shan Wu did looking at Nino 3-4 skill and comparing to DPLE skill. So this is looking at the SMILE November initializations. And as was mentioned in the plenary, we see some evidence of improved skill following strong El Niños. So we get a higher correlation in SMILE, which is black, compared to DPLE red, and we get a reduction in the root mean square error. On the flip side, we seem to do less well after strong La Nina peaks. There we go. And so here's a Hovmuller that kind of shows this skill improvement for 2-year La Nina events. So these are following strong ENSO events, and they're listed here, 1972, 82, all the way up to 2015. And so you can see for individual events like this 1982 2-year La Nina, SMILE seems to be doing a better job of predicting that, initialized in this November state of anomalously warm tropical Pacific, and DPLE did less well. We see similar improvement for the 2006 event. And so these are encouraging signs that we're still looking into. And a possibility for this improvement is the reduction in the cold tongue bias in SMILE compared to DPLE. So if you look at the drift, which is the lead time dependent bias as a function of forecast month in the Nino 3-4 region from SMILE in black, you can see that we're just not developing the same depth of cold tongue bias. And so this is a good sign because Shan Wu has a nice paper being prepared for submission that identifies this cold tongue bias as one of the main sources of error in our Nino related prediction skill, at least in hindcasts that were done with CESM1. And if we look at how that bias develops as a function of start month, we see that the strongest cold tongue bias is coming from the February initialization. But these late spring and summer initializations, May and August, have a cold tongue bias that doesn't exceed -1. And so this is a big improvement over the CESM1 hindcast that John has written up in her new paper. So there's hope that when we dig deeper into Smile Nino skill, that we're going to see some benefits of this lower mean bias. And here's another analysis that John Wu did, looking kind of at the broad picture of SST skill as a function of forecast season, again, comparing directly to DPLE. This is the difference of correlation skill, Smile minus DPLE. And this is again from just the November start date. And you can see, fairly high skill out to this second SON. Initialized from November, and the comparison to DPLE, looks good in the early seasons and then shows more of a mixed bag. I've also looked in very cursory fashion at the CI skill, and I have also compared this to the DPLE 40 member forecast. So this is looking at Northern Hemisphere winter sea ice extent. So this is in the first winter of the prediction. This is in the second winter. What you can see is maybe a reduced bias in sea ice extent compared to DPLE, which is getting too extensive, certainly by second winter. Seem to be doing a slightly better job in Smile. But if we look at summer, we see the reverse. So DPLE sea ice extent, this is actually the actual raw value, not the anomaly. The mean sea ice extent was actually quite good in DPLE in summertime. And so we made a concerted effort to try to maintain our sea ice thickness in Smile. And it looks like we might have overdone it, because now our summer sea ice extent is showing this too high bias in year 2. Here's an analysis that Isla produced. It looks at seasonal NAO skill from the November initialization and compares to DPLE. And this was a bit disappointing to see that Smile has a lower year 1 skill, essentially 0, compared to DPLE, which at least had something. So neither of these two systems shows any skill in the second winter of the forecast. So I wanted to mention the forward extension. We can easily extend the atmospheric initial conditions up to near present. So we've got those for May 2021. What we're trying to do in collaboration with Land Model Working Group people is extend this Smile trendy state reconstruction of CLM5 through May 2021, but we don't have the Smile trendy forcing. So we're thinking that we'll just switch over to JRA 55 forcing, which is available, and maybe try to do an anomaly forcing approach. So this is under construction. And then Keith Lindsay is going to extend the Smile Fosse run using JRA GoGo DO forcing that we are now able to get in near real time. And so we should be able to get this May initial condition within a week or 2. I mentioned this in the winter meeting. As far as the data release, we're going to follow the CESM policy, which says that this experiment will be available to any CSM working group no later than 6 months following the conclusion of the experiment. So that was last month. And then it becomes fully public as soon as the scientific paper has been submitted, or 1 year after the end of the simulation. And so a group of us have started putting together a Smile documentation paper. This is in preparation. It will give some, basic experiment description and a broad overview of skill. And we're hoping that this will also point to a GitHub repo of analysis scripts so that people can build off of the tools that we're developing kind of in our initial assessment of this experiment. And as I mentioned, the Smile analysis registry is becoming more important now that the data are close to becoming available. So please sign up if you're interested. We can make this link available. We can try to facilitate coordination within the group. There we go. So we already have some people who've signed up. Thank you for doing that. And, you know, as you can see, several people interested in ENSO. So hopefully we can get people to talk to each other and carve out some distinct research foci. So if you fill out this form on the spreadsheet, the more detailed you can make this, probably the better. You know, I would say maybe something as general as S2S might be too broad, but you know, we need to start having these discussions as we get close to working on this data set in tandem. Finally, I just want to mention some things about the ESP working group CSL allocation for year one, which spans November to October 31st of this year. We were awarded 17.6 core hours on Cheyenne. We're underutilizing this resource so far, and in part that was because the SMILE production was much cheaper than anticipated. We planned on having to use 10 million of the ESP working group allocation to complete SMILE, but we were able to run it quite efficiently and just use the NCAR Strategic Capability Award. And we've had slow progress on case studies and planned development experiments of the sort that Dan Emrine and Yaga have mentioned. So we started discussion on what can we do, what can we prioritize over the summer and fall to use up these resources. And as I mentioned, we're planning to extend the November start dates to start to form a CESM2 decadal prediction large ensemble. Right now, this is using Catalyst resources, so we're not using the ESP working group project code. And this SMILE forward extension I mentioned is going to be quite cheap, probably less than 1 million core hours. Yaga's S2S sensitivity experiments will, if we run these over the summer and fall, eat up about 3 to 8 million. Remains to be seen exactly how much those are going to cost. And so another option then is to just start a backward extension of SMILE towards 1958. And that would cost about 0.2 million core hours per year that we extend it backwards in time. We do have the initial conditions all the way back to 1958. So this is definitely an option, or we could add more ensemble members to the existing data set. So that's a discussion to have. And not to be prescriptive, but I thought it would be useful to at least put down some topics of discussion, maybe that we think it would be nice to talk about. How can we better involve the community? What are the obstacles and needs to getting involved in the working group? Are there additional experiments that should be prioritized that we haven't mentioned? We're interested in finding out who's willing to lead on some of these ESP working group sensitivity experiments that can leverage our new control experiments, these S2S and SMILE experiments. And finally, how to best organize ESP working group diagnostics development within the broader CESM diagnostics and Earth System data science initiatives. So we heard from Judith this morning about a package that she's been spearheading. Another idea might be to have a dedicated ESP working group GitHub repo where we could start to build up sort of a distributed, developed set of diagnostic tools. So I don't know if I've gone over, I hope I haven't, but I'll stop there and we can start discussion.
Thanks, Steve. So what I would suggest, if you're willing, turn on your camera. Would love to hear from you. And I will take some notes. So if Steve, do you want to moderate the discussion so I have time to type?
Yep.
Thank you.
So I see hands from Maria.
Yeah, hi, thank you. That was a really great overview. I have a question about the S2S and SMILE runs, and this is just more general, thinking ahead, whether this is on your radar or not. I know there's been an effort done for higher vertical resolution, but I was wondering if there's going to be an effort down the road for higher horizontal resolution. I know for sub-X protocol, that's like the 1 degree grid or so that you're following, but is that something that you see coming up in the future to try to assess the skill of horizontal resolution or the impacts of it? on skill?
That's definitely something that is high priority in the IHES project, which is the International Laboratory for High Resolution Earth System Prediction. Many of us in CGD are involved in that. And so we are doing FOSSI initialized decadal predictions at a 10th degree ocean resolution, quarter degree atmosphere. Those first sets of hindcasts are completed, and probably we're going to need the remainder of 2021 to fill out that that kind of base experiment. I don't know that there's any plans within ESP working group, at least not in our CSL proposal, to address the horizontal resolution issue. And I can't speak to sub-X, so maybe Yaga can answer that question.
Well, I think one of the issues is we don't have a high resolution CSM that's ready to go. And I think for the subseasonal hindcast to be useful, everything is done on anomaly. So you would have to complete the entire hindcast set. Although if there was a model ready, we could try to do a few case studies. But they would then have to be done, analysis would have to be done on the raw field. So I think the need for the hindcast is requires a lot of computation time. And I think then the other thing is, which model would we use for that?
Thank you.
Next up is Alan. We can't hear you. You're muted.
Yeah, the usual problem. I'm kind of new to this, but I didn't hear anything about volcanic eruptions. Do you put volcanic eruptions into your forcing for these hindcasts? And are you ready to put the next big volcanic eruption into the prediction runs that you're doing? Volcanic eruptions produce the largest forcing for seasonal to interannual timescales.
Absolutely. Yes, we do include them in these control hindcasts, so it's part of the forcing. And this is done so that we can directly compare to our uninitialized set that uses volcanic forcing as well, so we can isolate the impact of initialization relative to that control set. There's no doubt that large volcanic eruption would add predictability to the system. And, you know, there's a debate about whether the skill we do have in our decadal prediction system is really coming from the volcanic forcing, not directly in the model, but at least through the initial condition that we're, you know, the ocean initial condition has the imprint of that volcanic forcing, which is perhaps, you know, a really important part of the predictability. I would say with our near real time forecasts, we will be in a position to, you know, if there's a large volcanic event, put out a near real time forecast of how that changes our forecast. So the answer, I think, is yes.
So do you do any runs without volcanic eruptions to try and see how important they are?
Yeah, so we have done a set that is parallel to our DPLE, that's using CESM1. And this was a 10-member set that did not include the volcanic forcing. And so this is a set that we're actively analyzing. Shan Wu has a lot of really cool results that hopefully she'll share maybe at the next ESP working group meeting. Yeah, very interesting sensitivities there of whether you include or do not.
I'm asking because I looked at the large ensemble from a couple of years ago and found that it did not do, after El Chichon and Pinatubo, did not do a very good job of simulating winter warming. But if I used the AMIP runs where it specified SSTs, then it did an excellent job. And that was because the models weren't doing El Nino very well or doing the ocean very well. So I was just wondering, and I also was wondering, what forcing do you use? Do you use the data set that Mike Mills put together with Anya Schmidt for the past, and what data are you going to ingest for the future?
I'm going to defer to Gokhan as to which data set we use. So this is just the standard CMIP forcing data set that we use for CESM, and I don't know where that comes from.
I mean, it's just a standard one that we get from CMIP6, but I think my understanding is that, correct me, Alan, if I'm wrong, is it's not necessarily the data set itself, but how individual models, and Jerry can chime in too, are free to inject those sort of emissions in different places or different heights. And I believe how you do that can make a big difference, even though the modeling groups are using, let's say, the same data set.
Yeah, the Wacom can take SO2 and convert it to sulfate aerosols, and especially if you're using Karma, allow the aerosols to grow. And so there's different ways of doing it, or you can just specify
But just to clarify, we actually get the CAM6 forcings for some of the fields from our vacuum simulations. So in other words, we do the vacuum high top simulations first with all of those emissions. Then we get some of the data sets from vacuum in addition to the CMIP data sets for our low top version.
Thanks.
And I'll just add to that, Alan, that we were thinking with Mike Mills to doing the exactly studies you suggest, but the problem is for Wacom, we have hindcasts on a subseasonal timescale only for initial dates between September and March, because the focus was on the winter season, where a lot of the eruptions happen during the summer. So we do not have the historical record. So yeah, I'm hoping for a volcanic eruption that happens in the winter season this time around.
The aerosols last for a couple of years, so
they last for a couple of years, but it would be nice to get them initialized. You know, if there was an eruption, do it around the eruption time and do some simulations with and without.
Yeah, they tend to occur in April, so.
Yeah. Or we'll just extend our hindcast, but there hasn't been running the high top model because it's so expensive, hasn't been our highest priority, but we could try doing it in a low top version.
Gokhan had his hand up next.
Yeah, I was just, I mean, this is in response to Maria also, and just to add to what Steve said, CESM working groups, and in particular SSC, sort of, there was a conscious decision made not to create a high-res version of 2.0 or CSM 2 series, because thinking was that already work was going on with CSM 1.3 with AST and IHAS, and thinking was that it's going to cost too much time, it's going to take away resources from CSM 3 development, and the new science that come out of that may not be necessarily much added value to ongoing CSM 1.3 simulations. So at this point, all the high-res simulations are done with 1.3, and the goal is to directly jump to CESM 2.x as we develop the new model with the high-res model version. In fact, we are thinking of creating what I call ultra-high resolution CESM. We are trying to see whether we can get 5-kilometer resolution both in the ocean and the atmosphere, and that's getting into the non-hydrostatic scales, and that'll be applicable perhaps for short-term forecasts for societal relevant applications.
Awesome. Thanks, Gokhan.
Jerry.
Yeah, I just wanted to just chime in on this volcano issue because it's really turned out to be a pretty interesting aspect of the S2D prediction problem, especially for the Pacific. When we were first doing this, we thought including the volcanic eruptions of the hindcasts would actually increase skill because you'd have a known forcing. And so there was arguments about leaving the volcanic eruptions out when we were putting the CMIP5 DCP protocol together. We put them in. As it's turned out, there's been some studies done since then analyzing the CMIP5 and CMIP6 models that the ensemble average model response to a typical volcanic, explosive volcanic, tropical volcanic eruption is kind of a weak El Nino, kind of the first winter afterwards, and followed a couple of years later by a La Nina. So that's what the model is trying to produce in a kind of ensemble average sense. So if the actual sequence that occurs after a volcanic eruption in the observations goes along with that, if there's a weak El Nino followed by a La Nina a couple of years later, you're going to get great skill for the Pacific sea surface temperatures. But if the actual sequence in the observations doesn't follow what the ensemble average model is trying to produce, you're going to get really terrible skill. And this is what happened after Pinatubo and after Tverber. So in the initialized hindcast after Pinatubo, we get terrible skill in the Pacific for like the IPO SSTs. After Tverber, the same thing. And so these no volcano simulations, we thought, well, if you leave the volcanoes out, the verifying observations still have the effects of the eruptions in there. So that may cause problems too. But I think Jean-Lou's results and initially of the no volcano runs, you actually get a little bit better skill on average because you don't have these kind of conflicting influences in the tropical Pacific after volcanic eruption. So I think it's a really kind of a challenging problem because you may get better skill in some areas, maybe in the stratosphere and other types of things in the northern hemisphere high latitudes, but for areas in the tropics, tropical Pacific, and even connections to the Asian monsoons, it really kind of complicates the whole thing. So I think this is a really active area of research that's pretty interesting. And I think one way to get at it are these no volcano runs. And Matt Long just sent me something where it's he or somebody, I think, Gokhan, maybe they just did a no Pinatubo set of hindcasts just for that period. Do you know more about that, Gokhan?
No, is it the same as no volcano ones that Steve?
No, he said it was just a no Pinatubo, some other simulations. He just sent me an email on this a couple of weeks ago.
I can speak to that. That's the for a separate project we're trying to do 30 ensemble members where there was no Pinatubo run from CESM 1 LE to compare with biogeochemistry turned on in the ocean to compare the ocean tracer distributions. Because we took a lot of our observations in the early 1990s. Our first decade of observations occurred then. And so we're worried about trends being biased. But yes, but that's available, I think, to everybody who wants to look at it.
Well, just to elaborate on the Pinatubo and River responses, there was actually the opposite happened after Pinatubo and River. So there was, a couple of years after the Pinatubo eruption, there was an El Nino when the model response was trying to produce a La Nina, and after Tavurva, the same thing happened. There was an El Nino a couple of years after that eruption, which is when the model ensemble average was trying to produce La Nina. So that's why those eruptions really produced really bad skill for tropical Pacific SSTs.
There was a huge El Nino after El Chichon.
Right, and that one was better because it synced up better to what the model was trying to produce. So you didn't get a huge reduction of skill after Chichon, but it was just Pinatubo and Tavurva, and just depends on the volcano and what the internal variability is doing in relation to what the model ensemble average is trying to produce.
And was the large El Nino after El Chichon caused by the volcano or moderated by it or independent? The real world only has one ensemble member. That's also the problem.
Yeah, that is the problem.
Isla has had her hand up for a while.
Yeah, I was just wondering, I'm not sure if I fully grasped all the implications of Jerry's talk, but as we start to analyze the SMILE, do we need to, is like removing lead dependent climatology insufficient? Is that the conclusion, or is it only if we want to isolate the internal variability? Like, do we need to come up with a plan for how we're defining our anomalies in the SMILE?
Well, I first have to see the final version of Jerry's paper.
You're a co-author.
I think, we should proceed with kind of the standard lead dependent climatology removal for this initial assessment. I think that, is standard practice and is good enough for kind of a first order look at the skill. And it's easier to coordinate across everyone who's looking at different fields. And, leave kind of the second order investigation of that for later.
Okay.
Sanjeev?
Yeah. So yeah, it's great to know that SMILE is getting completed or not complete. While making the presentation for this workshop, I went to the US Drought Monitor, and it looks like there is a big drought going on in California and Nevada region. And what I have learned last couple of years doing different predictability analysis, that at least the CSM model has very large predictability compared to the other region in that particular, like California, Nevada region. So have anybody looked into, or is there some interest in the direction of what this drought was predictable using 2017, 2018 initial condition, and when this drought is going to go away, because that gives a kind of societally relevant angle to this project. And if we find something that can be a kind of quick or a small paper advertising this new set of simulation.
Yeah, so I don't know if Isla wants to jump in with an answer. It's definitely on our radar that we're in a position, if SMILE is skillful in the Western U.S., to actually maybe shed some light on what to expect in the coming year, right? So we just had a La Nina this past winter, and with our May 2021 forecast, we can maybe say whether we're going to see a 2-year La Nina and what the probability of that would be. That would be quite relevant and actionable. So we just need to dig more into the data. It's a bit too fresh to give you a hard answer.
Thank you.
Liz.
I just wanted to briefly comment that I'm really excited to see all of Judith's diagnostic package starting to come together. And it would be great to see that evolve, I think, into some sort of ESP working group repo that's a bit more flexible for different kinds of workflows. For example, I don't need the czar capability because I'm mostly working on Cheyenne. But some sort of package similar to pop tools, which I use for certain simple things that I don't need to calculate all the time, would, I think, be great. Stuff that can read in any type of CSM, ESP data sets, and then do all the difficult stuff under the hood as just simple functions. I'd love to see that happen.
I totally agree. I tried to get the ball rolling on that a little bit with just the internal SMILE group, to set up a repo where we could collaboratively develop, performant Python scripts. But it's hard. I think it's hard to, it kind of works when you're in a small project group and that's meeting regularly to do that. But when you're trying to co-develop with a large group of people, it gets complicated quickly. And I think we're still learning, what's feasible in that area. Certainly, I think if we can get Anderson to set up intake ESM to really efficiently read in these control data sets that we now have, the S2S and SMILE and DPLE, I think that'll be a big win. And that's the sort of generic tool that could maybe go into an ESP working group GitHub repo, and then we build from there.
I think that brings us to the topic, and I would love to hear from the communities how to involve you a little bit better and what are the obstacles and the needs. So that's the question for all of you, not at NCAR.
Okay, I don't have to answer anything then. Good.
Sanjeev has a hand up.
Yeah, that is a very good question. I'll try, from my experience, but in terms of the obstacle, it's kind of lining up the resources, and it requires a little bit broader push, not only from the individual PI, but also at the management level. Like when these big runs goes on, are there kind of smaller project allotted where individual PI can get graduate student or the postdoc to work on the at least 2 or 3 something interesting project. So from my side, it's kind of resource limitation is kind of one thing that I can bring in, and lining up with either existing NSF funding. If I go to the NSF, some project get funded, some other doesn't get funded. So and dependent upon the funding cycle becomes an issue.
So I understand that Eric DeRiever is very open to proposals on Earth system predictability as long as they are focused on research on sources of predictability, not skill, but understanding processes, etc. And we would be happy to, give you a support letter and make all the data accessible. So we've had 1 or 2 proposals, I think, have gone in the last 6 months to Eric on the topic. And just to comment on that, we don't have at NCAR we have few large efforts. So it's not so easy, I guess, for us to piggyback additional university collaborators, but there would be something maybe to think about in the future, how to do this. Because a lot of the efforts at NCAR are already a little bit underfunded and they rely on NOAA funds, which have been they've been super helpful, but they've not allowed enough funding that we can involve the university collaborator. So I don't know if anybody else wants to comment on that. Gokhan.
No, I mean, with NSF at this point, with Eric, his interests are mostly on the sub-seasonal shorter timescales, not necessarily longer timescales. And we need to be extremely careful not to step on operational side. So that is research to transfer is okay, but operational sort of forecasts are the sort of the boundary at this point.
Yeah, that makes sense. Thank you. That's why I said it's not individual PI or individual the scientist level to answer it, but it requires larger community effort to think about. Thank you.
And going down our list of questions, are there additional experiments that people would want to see or suggest or prioritize some of the simulations that Steve mentioned that we're going to keep doing? In particular, I think we were hoping to get, Nikki, go ahead.
I'm particularly interested in the extension through the present day, in particular because of the COVID pandemic and the effect that this may or may not have had on the climate system. And I think it would be interesting to investigate predictability in the context of that, just because it was such an unusual external forcing situation.
So can I say something with respect to that? Nikki, as I mentioned in the plenary talk on Monday morning, and John, I don't know whether Fasulo actually followed up on it or not, but we have actually, it's not predictability, it's not prediction experiments though. We have 50 ensemble members of COVID plus Australian fire and then the actual GFED fire simulations as well. So I'm not sure whether, and they are with the full CESM, if I'm not mistaken. So biogeochemistry is actually included in those. So if they are not the prediction simulations, so they are sort of short-term 5-year, 50 ensemble member simulations, if that's of use to you.
Yeah, I think that's interesting. One of the things that I've noticed is that certain modeling centers decided to do prescribed atmospheric CO2 and certain modeling centers decided to do prescribed emissions. And I think almost the prescribed emissions are preferred for this particular situation. So I don't know how that doesn't really fit into the SMILE, the way that SMILE has been run, because it's been prescribed atmospheric CO2, right? And the ocean and the land respond to that, but it doesn't affect the atmospheric CO2 in turn. And so that makes it a little bit more complicated. So I think there's something to be learned from the prescribed runs too, and something I want to think about, but I just wanted to put my 2 cents in that period of time is particularly interesting.
And then another thing that I should probably, it's not necessarily ESP working group thing, but it's on the climate variability and change with the CSM 2 large ensemble, and Ayla can chime in as well. We have now quite a few ensemble members with the same model of all but one forcing cases. So they're also with biogeochemistry that can be of use perhaps.
Yeah, these ones they're not the all but one. They're the only one of all.
Sorry, I keep getting confused with those things.
And
But if we run the, oh, carry on.
Go ahead.
Well, I was just wondering if we did run in these extensions, are they actually going to have the COVID forcing, or they're using like an SSP scenario?
Yeah, so that's actually what I was going to mention. So they would be using the scenario 3370, but John Fasulo had indicated interest in doing sort of a GFED sensitivity parallel to SMILE that would actually include the Australian wildfires. So, indications are that's a much bigger signal than the COVID emissions reduction, which we'd be missing in the SSP. But it'd be really interesting to see how the forecasts change if you add in these large aerosols from the wildfires.
And then one more complication is that the Australian fires and COVID protocols use SSP 245. And I believe SMILE and others are using 370. So there's also that difference between the two.
Yeah.
I think one other question we had, whether there are any community members who would want to look at particular case studies and either on the subseasonal or longer time scale do additional experiments.
And I think the carrot there is that, we could use the working group resources to support that kind of work. We just need someone to lead it. Pedro Denizio is not here. He had expressed interest in the winter meeting, so can follow up with him. But the idea would be to do, the sorts of experiments that Nick talked about in the first talk, relative, say, to SMILE, and see how, can we start to do some attribution of particular events on a multi-year time scale, in addition to S2S. Gokhan?
Yeah, I didn't join this working group meeting until last hour, but another opportunity if people want to propose experiments, if there is no computer time, is the upcoming ASD call that we can pursue. And those essentially can be up to whatever 50, 60, 80 million core hours on the new machine. And they can be essentially dedicated to particular experiments, but somebody has to lead those and everything needs to be ready.
All right, well, we're a little bit, a few minutes after noon. What do you think, Steve? Should we wrap it up?
Yeah, we can leave the Zoom call on for anyone who wants to chit chat, but if there aren't any more topics for discussion, then we can end it.
Bye.
So Sanjeev, just get in touch if you can, I don't know,